Check. Yeah, it's working. Okay.
Well, good afternoon, gentlemen. I think it's time to start. Welcome to the workshop, updated guidance on benchmark dose approach. We will have presentations this afternoon. First, I will back coming from in benchmark dose modeling. Then Mark on one side will introduce the new approach is published now, and then I think we are ready for a coffee break. And after that, Bernard will take us through the future, the new approach, and then Jose will introduce the technical part, how the platform works, and the preparation for the exercises of tomorrow. But before giving the floor to Nick Kritz, which is the director of EFSA's Risk Assessment Services, to welcome you all, I would like to ask you to put your smartphones on silent mode and not, if you have urgent phone calls, please do it outside. Otherwise, I think it should be. So let's hear from Nick de welcome. Please, the floor is yours, Nick. Hopefully the
Okay, I
technique
hope it works
works.
now, and you can all hear me. An echo? Or does it work now? Good,
Working.
okay. The technology works. Welcome to everybody there in the room in Brussels from also a sunny Parma, and thank you very much all of you for attending this workshop on the benchmark dose and the explanations of the third update to the benchmark dose approach and the guidance that was, of course, published late last year. I might look like a pilot, but think of me more as the steward that tells you to put on your seat belts and strap in for what will be 2 intensive half days, because you have, I see that there is, do you not hear me?
No, it's fine.
It's fine. Okay. I saw shaking heads. So if it works, I continue. So don't think of me as pilots. The pilots are there. Joseph is there, and Mark, and Jose, Bernard, and Marco that will guide you through what are 2 intensive half days on this workshop. And already Joseph has explained a little bit. The first half day spent on an explanation of the updated guidance that was published late last year, and really which comes and stems from something we discussed at the scientific committee this very morning, where also Joseph was there, which is the need to better harmonize with our international partners, whether that's the US EPA or Health Canada, WHO, and build partnerships and work on trust by using also similar, if not the same, methods. And here we have done this update, and this afternoon I think will be spent in providing quite some convincing arguments why we believe that the use of the Bayesian approach is the way to go forward, and also to bring in the probabilistic interpretation of results, as well as incorporate additional scientific knowledge into the modeling. This will all be explained in detail by the experts in order to then lead to hands-on exercises and examples based on pesticides tomorrow. I'm sure that will all interest you and really come with the aim or the result that hopefully we've provided enough arguments to show the value of using this updated benchmark dose approach compared to other alternative approaches that are also used. So with this in mind, I hope that you have a very insightful and successful workshop. I hope you also have a good time in Brussels, because that's important, and have some informal discussions and exchange of information in the margins of this meeting. That's also important, again, in the post-COVID era, to bring people together and ensure that when we talk about new approaches, then when we talk about updates, etc., there is enough soft communication also. That's why we did this workshop, to ensure uptake and successful implementation. So without further ado, I know you have 2 busy half days ahead, as I said already. I hand over to the chair of this session, Josef Schlatter, and wish you really a very good and constructive workshop.
Okay. I'm moving now over here because I'm the first speaker, presenting the past, how EFSA got involved into the benchmark dose modeling. And I would like, can you put up the slides, please? That's the technicalities. Now it's working. Okay. Yeah, so that's the title. Now, where is EFSA coming from? From the very beginning onward, EFSA was struggling actually with assessments of genotoxic and carcinogenic substances. Now, you may wonder, why I'm talking about this when this is a workshop on benchmark dose modeling. In the very beginning and before 2005, as you see on the screen, whenever a risk assessment was to be performed on genotoxic and carcinogenic substances, the assessors knew already the outcome before they started assessing all the information. It was, in my view, just a waste of time to pull all the data together, produce dozens of pages and reports when you already knew that the outcome would be ALARA. That was the word, as low as reasonably possible. That means any carcinogen, being a potent one like aflatoxin or a weak one like methyl-eugenol, the answer was always the same, as low as reasonably possible or achievable. So this is actually a risk management tool, and the reason for that was that the assumption is that there is no thresholded mode of action, meaning there is no effect level, there is no reference point, and that means also that the classical acceptable daily intake approach was not possible. In some parts of the world, they used low-dose extrapolation, meaning, and now we are approaching already modeling, putting mathematical modeling to the dose response data, and then extrapolating down to the human exposure level, which may be 10 or 12 orders of magnitude sometimes, and that results in vastly different so-called virtually safe dose. If you extrapolate down, for instance, to a risk level of 10 to the minus 6. And that's simply as good as tossing a coin if you have an outcome depending on models which may be different by 5 to 10 orders of magnitude. What would you do with that? And that's why EFSA then proposed to use the margin of exposure approach, comparing human exposure with a reference point. But what should the reference point be? And that is where the benchmark dose modeling came into play. The scientific committee proposed in 2005 using a benchmark dose approach to obtain a margin of exposure, which then, depending on the size of this margin of exposure, would allow for setting priorities. How urgent is it for risk management issues when you have a certain margin? And that was really a step forward. But that means also that in the beginning, this approach was only taken for unavoidable substances in food, namely mostly carcinogenic substances. That means also only or almost only for quantal data. The scientific committee recommended the BMDL, the lower confidence interval of benchmark response. I will explain later what that means, although I'm sure most of you here in the room will know what I mean by that. To use this as a reference point, and the reason for that was that this usually doesn't require extrapolating outside the observed range and mainly modeling the observed range. Software was available at the time, was mainly the US EPA benchmark software, which was already at the time available with an easy-to-use and user-friendly platform. The scientific committee already then mentioned clearly that EFSA would work on the benchmark dose approach in the future, and that led then to the first guidance document on benchmark dose modeling, which was published in 2009. This document was mandated to assess the existing information on the utility of the BMD approach as an alternative to the traditional used no effect level. And already this term of reference will tell you that the intention was to use it more broadly, meaning not only for quantal data and not only for genotoxic and carcinogenic substances, but more generically, meaning also for continuous data. The conclusion from the scientific committee in that guidance document was clearly that the BMD approach is a scientifically more advanced method compared to the no effect level. And if you are interested on the discussion on this, please go back to this old guidance document where you will find a lot of information about the comparison. What is new in here that using the benchmark dose approach will also, or does also allow a quantification of the uncertainties around the reference point established. And in a second step in that guidance document, EFSA asked also the question whether in which areas the BMD approach should be used. And the answer to that was it's applicable to all substances, irrespective of their origin, that this benchmark dose approach can be used. And thirdly, EFSA should give advice on whether the selection of the appropriate uncertainty factors are specific uncertainty factors are needed, because conceptually we switch now to a benchmark dose, which is defined by the BMR, which is a response level and no longer a no effect level. And that created some discussions in it. And last but not least, in that document, you will also find some guidance on how to use the benchmark dose approach. The NOAEL approach is looking at the highest experimental dose for which no adverse health effects can be detected by statistical means. And that's called, in the very early days, in the 60s, was a no effect level. But then it was realized that it should be called no adverse effect levels. And it depends, of course, by statistics to detect some effect. So that means a no effect level is not really a no effect level itself. It just means it's no longer statistically detectable. And in that sense, it's not really a conceptual difference to the benchmark dose, lower confidence limit, where you conceptually start with a predefined benchmark response, which should be somehow biologically meaningful. The benchmark dose approach used the very same data, but it doesn't look for a non-detectable effect, but is modeling the dose response data and aims at the predefined response level, the BMR. When doing so, this benchmark dose modeling allows also the evaluation of the statistical uncertainty of the estimate, and this is also the advantage, or one of the advantages of this approach. Finally, as I said, the same dose or the same experimental data is used. The problem is that all the OECD guidance documents on how to perform animal experiments, and we are talking here mainly on modeling of experimental animal studies, is designed to detect statistically effect levels. And that means you have quite frequently a limited number of doses, and that may pose a problem when you go into modeling. If you have a data set like it's shown on the right-hand side of this slide, then most statistical models applied to your data will be able to fit the data, and the resulting benchmark dose lower confidence limit will be very similar. However, if you have a data set looking more like the one on the left-hand side, then the models may behave vastly different, and the outcome and the uncertainty in the estimate may be large, so that you are encountering the problem which model you should select. Sometimes the best fitting model was selected, but that was clearly not the case what EFSA recommends, because EFSA recommended to actually use all the models which are compatible with the data at hand, because you have always some confidence around your data point and you can draw several lines through these data points. So there are two situations which may indicate that you have a problem with your data set, namely when you have very wide confidence interval, or when the different models result in a vastly different lower confidence limit between the models. And the recommendations at the time from EFSA was that if the difference is larger than 1 order of magnitude, then you really have a problem, and you should pose the question whether that data set is really suitable to be used in risk assessment. And also that you shouldn't extrapolate far outside of the observed range for the reasons I was mentioning before. There is a problem that in the early days, when the problems were arising with benchmark dose modeling, they just went back and chose the no effect level approach, at least for continuous data. And there, EFSA clearly said, you shouldn't do that. If you have a problem with your data set, if there is much uncertainty or too little information in the dose response data, then a weaker method is not solving the problem. You should solve the problem by hopefully finding a better data set. Now, coming back to the question posed by EFSA, as we are dealing with benchmark response, which is predefined, 10% in the case of quantal data or 5% in case of continuous data, do we need additional uncertainty factor? An analysis of roughly 400 NTP studies comparing no effect level with the benchmark dose lower confidence limit, in this case of 5%, the outcome was clearly that on average, these two approaches provide the same level of protection, meaning that there is no need to add an additional uncertainty factor, and the traditional uncertainty factors can be used. I need to say that at that time, the benchmark dose approach was mainly applied to cancer data, meaning incidence data, where this is not such a big problem because the detection limit is in this experiment around 10%. That's where the 10% is coming from. And with continuous data, it was mainly a 5%. For endpoints such as body weights or whatever you choose at the time, but in the meantime, more and more was the benchmark dose approach also applied, for instance, to other endpoints such as methemoglobinemia, and there it becomes much more tricky to define a BMR which is biologically meaningful. Just to give you an example, if you choose methemoglobin, the background level in experimental animals is maybe somewhere around 0.5%. So if you would choose a BMR of 0.5, that is a meaningless BMR, it's a meaningless increment in methemoglobin in blood. EFSA at the time chose 100% increase, a doubling. But to me, still 1% methemoglobin in blood is not biologically relevant. It becomes relevant when you're up to 7, 8, or 10%. Just to give you an example, it's not the intention of this workshop and talk on this, but this is just to remind you that this is a task for the toxicologists to agree on what is a BMR which is biologically relevant, and this should be on the border when an effect seen becomes adverse. This has nothing to do with the modeling, but of course this can lead to diverging outcomes if you use different BMRs as a starting point. Perchlorate is another example. WHO used 50% inhibition of iodine uptake. EFSA used 20%. And it's clear to all of you that then you will end up with different reference points. But as I said, in general, this should be not dependent on the uncertainty factors. Should be the same. In 2010, EFSA organized a working shop, and that was the first training course in benchmark dose modeling. And there also both quantal and continuous data were used to show how that works, and two different platforms were introduced. The one I already mentioned, the BMDS from the US EPA, but also now the PROEST from the National Institute for Public Health and the Environment of the Netherlands, which was also then later on transformed into the EFSA platform, which may be known to all of you. At the time, the recommendation was clearly that you should, as I already mentioned, consider all models which are compatible with your data and give a reasonable fit. And you should not aim at finding the best fitting model. And therefore, the recommendation was to use the lowest BMDL of all the models and the data set. BMD approach as a summary, as I said, it can be applied to all toxicological effects, and it makes use of the whole dose response data. It is critical that you select in advance a biological meaningful benchmark response. And then it's the BMDL lower confidence limit, which is usually selected as the reference point. And finally, that the BMD approach provides an evaluation of the quality of the data. And it sounds very simple. You have just to specify your data. Is it quantal? Is it continuous? That's not the problem. No disagreements there, usually. But the points in red, namely the specification of the BMR, as well as the selection of candidate dose response models, that created quite some problems in the past when doing benchmark dose modeling. Identification of acceptable models is also not that difficult, because that's then handled by the software, and the estimating the BMD and establishing a BMDL as the reference point is also not difficult, because you simply apply the approach to all critical endpoints and to all models. And for each endpoint, you select the lowest BMDL, and from all endpoints, the result, the lowest BMDL from all endpoint is then your overall BMDL to be used in the risk assessment. Already at that time, EFSA was aware that this can create problem and that selecting models may not be ideal. And there was already then on the horizon that something which was called model averaging was coming up, but it was not there yet and not ready yet to be implemented. But it already was said, please be aware whenever model averaging becomes available, this should be used to avoid that one organization selects one model and another select a different model, creating additional problems then. So it is preferable to have this model averaging, but at the time this was not available. Just showing you this dose response curve again, and I need this now because I need to introduce the problem of constraining parameters. You have A, the background parameter, this is clear what it means. B is the potency, is it 1 milligram, is it 1 gram, where the effects start. You have a maximum response, you cannot kill more than all animals, or whatever the maximum response is also quite easily understandable. But then is this parameter D, which is called the shape parameter. And this parameter leads the model behaving strange. Maybe for a mathematician it's not strange, but let's it call biologically not plausible. Namely, that depending on the data set, it may lead to a biologically implausible dose response curve, meaning that the steepness of the dose response, the D parameter becomes infinite when it approaches dose zero. That means zero molecule, zero effect. One molecule, you have already quite a high level of response, which is not really plausible. And there was a lot of discussion around this. And that led to constraining the model or not constraining the model. And that is a continuing issue, which then led to diverting opinions. Just again showing one example which created problems. This was the 3-monochloropropanediol issue, where the choice of the BMR was not a problem, but use of different modeling. EFSA, and if you look on the right-hand side, the data doesn't look that bad. But when you model this data, then some models behave exactly the way I described before, that you get a steepness which seems implausible and led WHO JECFA committee to conclude that is unrealistically low BMDL received when using unconstrained models, and they used the constrained models, and there it was just a logistic model which was fitting the data in an acceptable manner. And that's why then you get these kind of outputs, meaning that you have a 10-fold difference in the BMDL, just when you choose on a realistic data set either the constrained or the unconstrained model. By the way, you see something interesting in the JECFA. They already used model averaging, which was available for quantal data there. And here we are dealing with quantal data. The reason that the single model output is practically the same as the model averaging is just that all other models but the log logistic model didn't fit well, got such a low weight that they didn't influence the outcome. So here is just one example. That led finally EFSA to update the guidance document on benchmark dose modeling. And in 2017, the most of the modifications made were providing guidance on how to apply the BMD approach in practice, recommending model averaging, which was then in a good shape and applicable, at least for quantal data, but also meaning then more technically now to use the Akaike criterion to use the goodness of, to judge the goodness of fit of the models, which is a combination of the log likelihood and the number of parameters, which is, I think, then also coming up later on. As I said, the main issue was to give better guidance on how to apply the approach, and there was a flow chart introduced. You see it here. I'm not going into detail too much here, just to highlight the orange parts to indicate that the software had, something happened. Yeah, it's back again. When there might be problems in the data, and as myself, I'm not the modeler, I'm therefore dependent on the software that I'm alerted when my data set gives some problem, and when you are better off asking a specialist in benchmark dose modeling whether or not you should use that data set. The red one is just a test whether there is really dose response information in your data. And then you see on the right-hand side, there is still the option to select a specific model when model averaging is not available. But once model averaging is available, this shouldn't be used any longer. That's where we were in 17, and in the meantime, it's almost exponentially the use of benchmark dose modeling, at least within EFSA. And the problems, some of the problems still remain. As I said, BMR, the choice is still an issue. This is not, as I said repeatedly, the core of this part. That's something for the toxicologists to struggle with. But the constraining, non-constraining the parameter is still there. The different sets of quantal compared to continuous data was still there. For the continuous was basically just 2 families of models, while for the quantal data, I believe it was 8 models. And there was still some controversy whether that couldn't be unified. Now, I'm coming to the end of my talk. This is now coming to the future. There was a conference held by WHO to update Chapter 5 on dose response modeling, where some international agreements were taken, and that was the trigger for EFSA again, updated 2017 guidance, and led to the guidance we are talking about today, and also to harmonize as far as possible the EFSA platform for benchmark dose modeling with the US EPA benchmark dose modeling, so that irrespective of use, either BMDS or the EFSA or PROST, that you should end up, at least for one data set, when using the same approach, that you should end up with the same outcome. So harmonization is the big word. It will probably not solve all the problems, but hopefully some of it. And here we are. By the end of last year, EFSA published this guidance of 2022. The main difference is that it changed from frequentist modeling to Bayesian modeling. And as I said, the 2 different sets of models for quantal data and for continuous data are uniformed and there is now a proposal of one single set of models, and this is now really the end of my talk, and will be the issue of the following presentation. Thank you for your attention. Are there any burning questions already now? We are looking in the past, and I didn't say anything possibly new. It was just history. So let's spare a few minutes for Mark Ertz from the Hasselt University, who has really a big job to introduce you to the new proposed Bayesian modeling, which is outlined in the new guidance. And I give the floor to Mark.
Right, it's already working. So good afternoon. Well, it's my objective, and it is a challenge to give you some more insights in the methodology, statistical methodology, so that it's less, possibly not anymore that kind of box. Something goes in and something gets out, so that you get more insights in what happens in the box. So here, this first slide is a list, and it has been mentioned to a large extent, of what's new in new guidance and in the new implementation. First of all, it's not a change, not a different direction. I would rather say it's a continuation of the previous guidance and software. It's important to say, I think, and it's a kind of extension. So the similar type of models, and it's about model averaging. So these basic methodological concepts and procedures are followed as well. What's then the extension? Well, we looked at more candidate models, because one assumption or requirement of model averaging is that the suite of models you're going to fit is rich enough so that at least one good model is there, because if all models are poor, of course, the average will be poor as well. The other thing which is new is the Bayesian implementation, which you can also look at as an extension of maximum likelihood. We'll go a bit into that more detail, but it also has the advantage that interpretation is more natural. The quantities which are playing a role also in the averaging feel quite natural. And of course you have what's called the priors that play their role, and the posteriors, and we'll come back to that later on. What's also new as compared to earlier versions is that we provide what we call preliminary tests. They go into assumptions and they check, let's say, whether these assumptions hold. Because there are assumptions floating around, and it was not really like a habit, so to say, that these were tested or checked. And so we provide more tools there. It's computationally efficient and sufficiently fast, we hope, and also the interface has been updated. And the idea is also to be fully transparent there. All methodological and technical details are available, and if there's need for more details, I would say just ask and we'll provide. Okay, this is the outline, and I'll start with the main statistical methodology, and that's the components of the dose response model of the models we apply. And roughly, you could think about there are two main components. That's the distribution of the response of the endpoint of interest at a fixed level, dose level. That's what we call X. So Y given X is a mathematical notation for saying you look at the response, vertical line, sorry, going fast, at a given level of X. Then we also have to describe how that distribution changes if the dose, for instance, gets larger, if that changes. And there the focus will be on the median. The figure below just wants to emphasize that building models is always a challenge. You want to be as accurate enough. You want that models fit the data well, but you also have to be careful of not overfitting the data. So simplicity is the other side, which is also very important. So it's looking for a kind of balance. So what do we mean by this Y given X, the response at a given dose? Let's look at an example. This is one of the examples in the guidance. It's a simulated data set. We'll look at others. But the simulated data set has the advantage that you know the truth, so you can compare with what the truth is. That's not realistic, but insightful. Now, what do we mean by this fixed dose? So here you look, for instance, at dose 1, just to take one of them, and you look at the vertical variation of the observed response values. That's the distribution we are talking about. And so it's already one assumption that this distribution is not changing when we change dose. Could be that at dose 0 it's a normal distribution, and at dose 3 it's a log normal. No, we are not going to do that. That's too complex. So the distribution itself stays the same across all dose levels. That's one thing. Often we don't have this kind of individual data. Mostly we have just a summary statistics, which are typically the arithmetic means and standard deviations. So you only see this. Of course, I think you agree it's more difficult now to get insights in this vertical variation, that distribution is behind that bar you see, because you don't see data. So for summary data, it's a bit more difficult to check it, but you still can do something, as we will see later on. So, what choices did we make? It's a limitation, but it's already at least two options. We look at, for continuous responses, the normal and the log normal distribution. These are obvious candidates. They both have two parameters. We'll come back to that later. For the quantal binary type of outcome, an adverse event happens yes or no, there's only one distribution, the binomial or the Bernoulli distribution as it's called, and it has only one parameter called pi of x, which is the probability that the event happens at that dose level. And there is extension to a bit more complicated situations when we have clustered observations and, well, there could be covariates. Now, let's make it a bit more concrete. So we look at the highest dose. It's like the maximum response in some sense, if that's reached over there. And we just look at those data, and we think about the distribution. So the first component we have to specify, so to say. Here are data now again, but across the horizontal axis, as well as a summary bar. And we've put there a histogram on top of that. A histogram is something we can use to get insight about that distribution. Now, a histogram is not always the best thing to look at because it can be also a bit misleading, or it can be unclear. It depends on where the class boundaries are, etc. But anyway, we can fit the best normal distribution to that. That's this solid line. And there is the other candidate, the log normal, so we can fit the best fitting log normal as well. They're pretty similar, I would say. So in this case, it's hard to distinguish and to make the choice. Now, we know the truth in this case. The true distribution is this one. Data are generated from this green one, which is a log normal. So with individual data, you can do something, but it's depending on the number of observations, of course, to have enough power to have evidence in favor or against one of the two choices. We have two choices. They are different because one is symmetric and the other one is right skewed. And so we see them as representatives of two types of distributions that can appear. This is another data set, and that's a real data set about fetal weight. And here we can do a similar exercise. We can look at the background response, let's say, the lowest dose level, the 0 dose level control group, and do the same thing. So we look again, and again we have those two fitted distributions, the normal and the log normal, that look pretty much alike. The histogram seems to look nicer, and you could say visually, well, not that bad. Perhaps we can take the normal or the log normal or both. This seem to fit reasonably well. Well, we want to provide a bit more there, a more formal way of checking whether these distributions hold or whether there's evidence in the data against one or both of the distributions. You could say, well, we're typically looking at positive endpoints. The normal distribution, well, it has a probability that it takes negative values. That's right. So here, for instance, you could look at the fitted normal distribution and look at the probability that the weight is negative. So I would say, well, that's small enough not to worry too much about it. It's ignorable. The log normal can take also positive probabilities of a weight more than 50 kilograms. That's not really what you expect for fetal weight. So you have to think about distribution always as mathematical approximations of a true distribution, which is probably more complicated than any of our mathematical models. Okay, so again, those two distributions, and then we close the story about these two distributions, but I just want to pick into the notation. There are two mu's, so both have two parameters, the mu parameter and the sigma squared parameter. We know for the normal parameter, the mean is the mu is the mean of the endpoint of the response, and sigma squared is the variance. Now for the log normal, the mu and the sigma squared are not the mean and the normal of the variable your response. They are though, and that's actually the definition of the log normal. That means that it's normal on the log scale. So the mu and the sigma squared refer to the mean and the variance on another scale and not on the original scale. That's confusing. So just this quick table, we are not going into the formulas, but if you look at the first column for the normal distribution, the mean and the median are the same because it's symmetric. Okay, that's one parameter for the central location. If you look at the second column for the log normal, the mean and the median are different. So you have two different measures for the location, and you can see, of course, that the mean is larger than the median because it's pulled to the right by outlier. Log normal is a heavy tail distribution, so it has outliers, and we all know that means are sensitive to outliers. So we will focus on the median as a parameter for both distributions, and it's the mu for the normal and E power mu for the log normal. You see that the variance in the first column, sigma squared, is what we expect, the variance of the normal, whereas the expression for the variance of the log normal is pretty complicated. Both parameters play their role there. And then there is a coefficient of variation, which is, by definition, the standard deviation divided by the mean. And that's what you see in the first column for the normal. And if you apply that for the log normal, you have this other expression. But what you see there, so to the right at the bottom, the coefficient of variation for the log normal, is that this doesn't depend on mu. That's constant if the sigma squared stays constant. But we'll come back to that later. Okay, so these are the final slides about this. So as we said, the mu and the sigma squared for the log normal here are actually on the log scale. So if we look at the normal here as an example with mean 7.5 and standard deviation 1.5, then you might say if you take the log normal with the log of these two expressions, so that means the log of the mean and the log of the standard deviation. That's like exponentiating back to get to the original scale. As we said, the mean is not equal to 7.5, it's a bit larger, but the median is 7.5. So median is a nice parameter to look at, which is more like a common thing across those two distributions. That's why we focus on the median. Then we come to a second component, that's about that median. And now that depends on x. So we have our table here. Now that's the only parameter, mu, that starts depending on x. Okay, for both distributions. What does this imply? Of course that the median, so the central location, can go up for an increasing response as those increases. That's what it should do, of course. But we see, for instance, for the normal distribution that the variance is not changing with the dose. So for the normal distribution over here, that sigma squared does not depend on x. So that means that for the normal distribution, the spread, the vertical spread across the dose levels is more or less, of course, data vary, but is constant. That's called homoscedasticity. Difficult word if you try to pronounce it 3 times. It's saying the scale is the same. The constant variance assumption. That's what we can test, even with summary data. You don't need individual data to do so. So this gives you a way indirectly to test for normality by checking whether the homoscedasticity assumption holds. For the log normal, in the second column, you see, of course, that the variance is not constant, but the coefficient variation is constant, this one, because it only, depends on sigma squared and not on the mu. I need my gin. Okay, and so also there we can check that assumption. So we can, for individual data, we can check really for log normality with the classical tests, but summary data, we can check log normality by checking whether the coefficient of variation is constant. Okay, this slide as such is just to relate our median to the BMD for continuous data, where the median is mu of x or e to the power mu of x. And for quantal data, quantal response, we have the other definition, where the probability at those x comes into play. Okay, here we have our candidate models for continuous data. 2 columns. The first column here is for normal data. The second column is for the log normal distribution. In the middle one, for normal, we have mu of x. For the other one, we have e to the power mu of x. Not going to go through this table, but you see that they all have 4 parameters, A, B, C, and D, right? We'll come back to that later. We have family 1A, 1B, and 2. You can see family 1A and 1B, the structure is everywhere the same. If you look at the middle column, it's A, brackets, 1 plus C minus 1, etc. Okay, so that's why that family is over there. Family 2 is structurally different. But that's all of the models, 16. 16 candidate models, 2 times 8. Now, if you would look at the previous guidance, and this is for me a quick slide, I just want to explain that, for instance, if you look at the exponential model, that's this one, and you look at the formula and the previous guidance, you would have a different formula. But that's just rewriting. Yes? So these are exactly the same. This is just a calculus exercise that explains this. All right, now for all of the models, whether it's family 1, A, B, or 2, A and C determine the background and the maximum response. For instance, for family 1 and normal distribution, A is the background parameter, and A times C is the maximum response. And B and D determine the functional pattern, monotone, how it goes from that background to that maximum or minimum for increasing responses. Now, it's still difficult to think in terms of these parameters if they are not really referring to the response or endpoint of interest. So all models are reparameterized in terms of these natural parameters. A, B, and C are reformulated, transformed, so that the model is defined in terms of background response, maximum response, and BMD. Okay, so forget ABC, think about background, maximum, and BMD. The D parameter, we call it more the technical parameter. It's not related to a unique characteristic, which is not depending on the model, but unique for the endpoint. The natural parameters are like that. That's a bit the technical difficulty with the D parameter. The variation parameter, sigma, could also be a natural parameter. We put it there in the technical parameters. Okay, a bit more about this D parameter. This is actually the model where we generated the first data set with. It's the exponential model with background 7.5, maximum 15. The BMD corresponding to a BMR of 0.1 is 0.229. As you can see here, I touch the screen or the pad here, you can see this is the BMD, and the choice of the D parameter is 1.8. So what happens now if you keep everything fixed and start playing with the D parameter, just to get a feeling what this D parameter is changing the model? Well, here is our generating model again, where D is 1.8. So if we have these equal to 1, the curve looks like this. The rest is the same. Background, maximum, BMD is exactly the same. This is for D.5. This is for D2.5, and this is for D5. So it determines actually like the steepness or the slope at the BMD. So if you look at the BMD here, the curves are getting steeper and steeper. The slope changes with the D parameter. So it has an interpretation, but it's difficult to relate this right away to a characteristic of the endpoint, especially as we will see it has a different value for different parameters. Why this slide? Because it looks a bit odd. Well, this is just to point out, if you look at the models here, D.5 and D is 1, you might say, hey, wait a minute, this is not reaching the maximum of 50. Well, the maximum of 15 is the maximum value, possibly for very high doses, further than your maximum dose, experimental dose. That's why, if you look at the next slide, the range goes up to 100, much further, and the curves are the same as you have seen on the previous slide, but you see now much more that indeed all models reach that maximum of 50. Okay, now we do a kind of other exercise. We take again that model where background, maximum response, BMD is fixed, and D is 1.8, and it stays 1.8. We're just looking now at the different models with exactly the same values. So these are the 4 models for family 1A, which all have the same values for the 4 parameters. We're looking not at variation, we're just looking at the curve. So it's not that these models, if they have same D value, that the models are like the same, right? Or that the slope or the steepness at the BMD point is the same. That's not. If you look at the other models, 1B or the models 2, then you see that E is making it more difficult because it's not something unique related to the endpoint. All right, now quick word about the quantal response. We have 2 parameters less. That makes life a little bit easier because there is no variance parameter. It's only the probability of the adverse event happening at a particular dose. And the maximum response is fixed, is equal to 1. Again here, a calculus exercise just to show that if you remember previous table for continuous response, there was the structure of A between brackets 1 plus C minus 1. You don't see that structure here. That's because C in this case is 1 over A, for instance, for family 1. And so you can rewrite things again. Nothing new. There is a parameter less, and that's what the result of that is. Okay, this was my first part, and I thought perhaps people are still awake and have interest in a question. So, an urgent question, perhaps? Question?
Hi, Mark. Thanks for the interesting presentation. I'm Gonçalo from RVM, the Netherlands. So, as you know, we have expressed our concerns and reservations of this new approach, but we're still very interested in, the situation and progress here. So my first question is, we see that the benchmark response is defined as the relative change, the background level. So that means we look at the response on the ratio level instead of on the original level, the response. But then in that case, I was wondering why would be normal distribution is illogical in this case? Does it conflict with the definition of the benchmark response? A related question to that is, in the example, we see that indeed the very small part of the response that is be negative, but when the standard deviation, or say coefficient of variation is large, then there might be some reasonable part that is actually negative. So what could be the explanation for that part?
Okay, so thank you for your questions. First of all, I don't see any conflict with the definition of BMD in a relative fashion with the normal distribution. I don't see a conflict with any distribution I could use, like the gamma or inverse Gaussian. So, yeah, we could start with a technical discussion, but I don't see a conflict. Regarding your second question, and we'll come back to that, this fits perfectly in the Bayesian context. If there is, we'll talk about this later on. I mean, if there is prior knowledge, if you have scientific evidence that the normal distribution, or in other case, the log normal, is not appropriate, you can put a prior on 0, and it will not play. So it's an extension which allows you, based on scientific evidence, to say, okay, in this case, the normal distribution is not a good choice, okay? And that's why we also have provided now these preliminary tests. It can help the user as well, because these tests, if that's the case, will indicate that there is a problem with the normal distribution, okay? Moreover, as we will see, and that's a nice experience we had repeatedly, if one of the distributions is violated, the weights, the posterior weights, are 0, and they are cancelled out automatically. So I don't see a problem with a situation where a distribution, in this case the normal, or could be the log normal as well, is for a particular endpoint a difficulty or a problem. Because if that evidence is there, it should be used. That's the philosophy of the Bayesian context. And that's also what we have shared in our communication with the idea to have harmonization with the US EPA. They follow the same idea here. Okay, okay, I think I am a bit under pressure, as you can see. I hope you didn't look at how many slides I have, because you're all looking forward to the coffee break. So let me continue. I would, with pleasure, like to introduce you more the basic concepts of Bayesian inference, because I think this is the most important change, and change, again, not the other direction, but a continuation and extension of before. So it's an extension of what we used to use, what we called maximum likelihood inference. And even that might not be so familiar to you. I hope it is, because what is this? This maximum likelihood estimation or inference. I will look at it and repeat it quickly as well to get to the Bayesian context. But the main point is that also the parameters get distributions. Everything gets a distribution. So the BMD gets a distribution. The background parameter gets a distribution. And what does this distribution mean? It has a very intuitive interpretation. It summarizes the knowledge you have about that parameter. Yes? So a broad, flat distribution says, I don't know much about this parameter. It goes about here to there, and that's all I know. Okay? And that's typically our prior distribution. Prior refers to prior to the analysis, prior to the data, even before the data were collected, possibly. But then we have data, we do the analysis, and that prior is then updated, revised to a new distribution, and that's called the posterior. That again summarizes our knowledge about that parameter. And that's what we hope, of course, that there is enough information about this parameter to make it more peaked, focused, smaller range, because then it says this is where the parameter, the true parameter, is laying somewhere, most likely under that peak, and I have a much smaller range. Okay? That interpretation is only holding in the Bayesian context. If that interpretation is given in a confidence interval for the frequentist, as we say, or the likelihood context, if a student says that to me, the lower limit means that the probability that the true parameter is only 5% small left of that lower limit, I have to say, you failed, student. This intuitive interpretation holds for the Bayesian, but interpretation for the confidence intervals we are used to, it's much more unnatural. It's referring to repeated samples. Out of 100, about 95 or 90 would contain the parameter. That's much more artificial. So that's an important pro for the Bayesian context. Let's look at an example. So we look at quantal data in this case, and we look just to focus on a very simple setting and to explain the Bayesian paradigm a bit more, just at the background response. So at those 0, we see that there are 6 events out of 50. Now, what would be the probability of the background response? I think you all would say 6 out of 50. Okay, 0.12. That's what we call the frequency estimator. We all know that. 6 out of 50. But then what you are now using in the previous guidance was a maximum likelihood estimator. Now, what's the maximum likelihood estimator? Can anybody say this? Well, what is it? Yes? Well, it's based on what we call the likelihood function, and that expresses the probability to observe the data which you observed as a function of your unknown parameter. Wow, that's something. Let's look at the example. This is the likelihood function for our data, 6 out of 50. That's built with the density function we have for our response. In our case, it's the Bernoulli distribution. That's a technical matter. That's just some maths. Okay? If you have a normal distribution, we can make this figure as well. For instance, how likely are the data I observed 6 out of 50 when the true probability is 0.4? Well, it's almost 0. Okay? What's the probability to observe my sample 6 out of 50 when the true probability is 0.2? Well, it's a bit more, but it's not that much neither. It's the highest probability to observe what we have observed is at 0.12. It's exactly the same as our frequency estimate. So that's why those two are so close. And it's not for all cases exactly the same, but they're typically very close. The frequency estimator or the moment type of estimator and maximum likelihood type of estimator, and we can construct the confidence interval. Okay, now we're going to the Bayesian. I know you all love formulas, so I thought once in a while a formula. And I really hope that you all got a probability course somewhere. And it would be great if you say, hey, that formula, I remember it. Well, we are not going into it. But it's the Bayes formula for conditional probabilities. And now parameters and data get a distribution. Everything gets a distribution in Bayes. And you can reformulate that formula in terms of parameters given the data, data given parameters, etc. Now, the next line, the third line, is the key line, which is the engine of the Bayesian paradigm. So this here, the distribution of your parameters as such is your prior distribution, okay? In case you have prior, before you have the data, not much of an ID, it's something flat, white, okay? Then at the other side, in red, you have the posterior distribution. It says, what is my distribution for the BMD given the data? After having applied the data, how does the distribution change? Okay, so you go from the prior to the posterior, and what's in the middle, the blue one, that's the probability to observe the data given your parameter. That's what we looked at in the blue curve a moment ago, you know? That's the likelihood. So the likelihood turns the prior into the posterior. There's also this denominator that's called the marginal likelihood. That's not depending on the parameter, so it doesn't play a role here. That's why we said here proportional to instead of equal. But it does play a role later on for the posterior probabilities. It makes it more complicated, this marginal likelihood. And that's why we have implemented two methods to get the posterior probabilities for the models. But I'm running ahead and making it probably more complicated. So we have data prior to posterior. Let's do this exercise. Okay, some exercise. Okay, we have our data, our background response, 6 out of 50. The blue curve is our likelihood. We've seen that before. The point estimate is where the vertical line is positioned. It's 0.12. Now we start with a flat, uninformative prior for our background probability pi of 0. That's the black flat line over the whole interval 0 to 1, okay? It's lower because, as you know, the area under a density is equal to 1. All right, so these are the two quantities at the right side here, the likelihood and the prior probability, visualized for our simple data set 6 out of 50. Now we go to the left-hand side, the posterior. We apply this nice formula from your course, and then you get this. Well, the posterior is the same as the likelihood. Yes? It didn't change anything. And where the posterior reaches its mode, that's your point estimate. So the point estimate is exactly the same. it's also in the Bayesian context 0.12. Nothing changed. But you didn't add any additional information by this prior. It's nothing additional to the data. So why would it change? Okay. Also, the confidence interval is not exactly the same, but it's very close. But it has also a different interpretation. It has a much nicer interpretation. There is 5% or 10% chance, about 5% in this case, that the true value is less than 0.066. That's something you should not say, certainly not as a student, because you would fail, for the left limit of the blue confidence interval. Okay, that's uninformative. And this is just an illustration that if you use an uninformative prior, look at the middle line, the Bayesian estimation is expected to be close to the frequentist estimation because you don't add anything. That's the idea about Bayesian inference. You have the data, but you might have other information as well. You might have another study, historical data, and you're not using it, although there is knowledge from that study, and you would like to include it as well. That you can do in a Bayesian setting with an informative prior rather than another uninformative prior. So in the bottom line, you see we can insert other information in this prior distribution. Well, where can it come from? As I said, historical data, literature, reported estimates, confidence interval, expert opinion. And of course, it should be determined before the analysis. It's something which is not based on your real data you want to analyze. It should not be based on the 6 out of 50, because they play their game through the data. You should not use them twice. Of course, it should be a well-taken decision, motivated to say, okay, I go for this prior, and it's a good habit, as we will show, of course, in a very simple way. The sensitivity analysis is a good thing to think about. Now, let's suppose that for our case, we do have an historical data set that gives us information about this background response at 0. And suppose that was another study where one found 10 adverse events out of 100. Okay? How could we use this historical information to feed that prior into an informative prior? Okay? Of course, you have to consider or examine whether these historical data are useful or the experimental conditions similar, etc. Species and whatever is relevant. So this is a kind of cycle of Bayesian updating, accumulating knowledge. So we will illustrate quickly, and it's not a unique way to do it, but it's making sense, how you have the historical data. Okay? You analyze these historical data using an uninformative prior, and you get a posterior. This first line in this scheme you can do already, and we can do this for many studies we have to be ready to be used for new studies. This is without the new data you will have to analyze. But you can then use that posterior to inform this informative prior, which you use for the current or the new data to get your updated posterior. Let's give it a try. Okay? So what we do, what I have done, and you'll see a visual representation of that in a second. So I've done here this first line. I have used an uninformative prior, as I've done before, on the historical data, and I get, of course, a point estimate 0.1, 10 out of 100. And this, I took now a 99% confidence or credible interval. For Bayesian intervals, it's called credible interval rather than confidence interval. And that 99% is 0.044.2. This is more or less saying what the minimum and the maximum value I expect for my parameter of interest. We will use, or we have implemented and used the PERT distribution. What's the PERT distribution? Here you have a picture about it. It's on another scale from 0 to 20, but that doesn't matter. So it has 4 parameters. It's minimum value, it's maximum value, it's most likely value, the mode, and then the kind of shape, the peakness. Okay, and that's a shape parameter. And here you see 3 PERT distributions with the same min, max, and mode, but 3 shape parameters. The shape equal to 0 is meaning I don't know anything more than between min and max. Shape equal to 1 is saying, well, I do have some confidence in that mode, that it's really most likely. But I can express this confidence, so to say, that it's really about that value much more by taking shape as 4. Okay, let's try it here for our situation. So we have this confidence interval, credible interval, from 0.044. So let's take this as minimum. That's why I took such a high credible interval, 99%. And the max is 0.2. The mode is my point estimate, 0.1. Now I'm looking at the shape. So I took the posterior. This is the posterior for the historical data. This is nothing about the new data. I had my historical data. So again, this is the first line here of this scheme, the top line. I have this posterior. Now you're looking at that posterior, okay? And I want to match a prior, PERT prior to that posterior. I already fixed the min, max, and mode, and now I take shape 0. That's this one, okay? Well, it's saying where it happens. It says where I am sure about based on my historical data, but I might perhaps take shape equal to 1. Or I could take shape equal to 4. And with the shape equal to 4, I'm very close to my posterior, okay? So that might do the job, because this is summarizing my knowledge I got from the historical data in this type of PERT prior. Let me now do the analysis, and let me go back to this scheme. Now I'm looking at this line here. I built my informative prior, and now I'm going to use that prior to get my updated posterior. Then I get this. So again, the blue curve is the likelihood, yes, where point estimate was 0.2. Previously, if you still remember, I have a black curve, which was a uniform, uninformative prior, which was just a low horizontal line. Now that's replaced by my informative prior, which is this one. The vertical scale is a bit different, but look, it goes up to something like 13. That's the same what you see here. That's the black curve. And those two, the black and the blue, are the right-hand side, if you remember, of the formula, and they are used together to get the posterior. And that's the red curve, okay? Now, what do you see? Now, the red curve is different from the blue one. So the posterior is different. The Bayesian result is, as you can see, different from the MLE. It's smaller, 0.109. But how does this come? Because of the informative prior, which has pushed everything a bit lower. There was information in this prior which is combined with the data to get to this confidence interval. The Bayesian credible interval, as you can see, is less wide. The lower limit is higher, the upper limit is smaller. So you have added information to the system that led to a more precise result. And that's, of course, the way one might want to go. So this is a kind of sensitivity analysis, if you like, with different informative priors, and you can see by looking at this ratio how the results get more accurate, and of course you can think about which choice is the most appropriate in the end to report about. This is not the only way to build a informative prior, but it is a reasonable way. And let me close this part to have some time for questions as well. We don't want to do this for one parameter only. We want to do this for our whole model, which has 4 parameters. But we can now think in terms of the natural parameters, the background, maximum response, the BMD, and then this D technical parameter. Okay, and here it's more a challenge than in the simple previous case. But based on our simulations we did, the best performance was reached with this PERT prior because we started with normal priors. And these normal priors are still acting on these technical parameters, D and sigma squared. This is a slide which provides the default uninformative or weakly informative priors. So for the BMD, it's a flat uniform prior from min-max, which you provide in your informative prior. But for uninformative prior, it's like the full range of the experimental dose or extended. And the default is that it is extended to that maximum squared, because depending on the design, it could go beyond your experimental dose. And it doesn't hurt to make it uninformative and stretch it a bit further. The other, this is the most important prior. The other priors do have a little bit effect, but to a lesser extent. We can go into this slide in more detail, but let's look at what happens. This is with the default priors, okay? We took a BMR of 0.1, and this is the fitted inverse exponential model, one of the models. And you see the BMR is 3.99, and the confidence interval goes from 2.6 to 6.09. This is this posterior distribution for the BMD. So each parameter, the 3 natural parameters, have a prior, turns into a posterior. We could show, and we will show the others as well, but this is the most important one. This is, again, the fitted curve, and this is the posterior on the BMD, and this is the credible interval, 5% left and 5% to the right. You might say, well, this looks more than 5%. If this is 5%, this has to do with the changing horizontal scale, which is not equidistant. But these are the figures which are shown by the application. Here you see for the quantal data, for the 3 parameters, in blue, it's the weakly or uninformative default prior. The most important one is, again, for the BMD here, which is as flat as possible over the whole range. And you see how this flat prior in blue by the data is turned into the orange kind of posterior prior. This distribution summarizes your knowledge about the unknown BMD. Okay? And the more it's peaked, the more accurate that is. Okay, let's look at 2 informative priors. One is very close to what we expect, so that's in line with the data, and the other is shifted to the right. You can see they're all values more to the right. It are these 2. So the black one is the default prior, as flat as you can think about. Then we have a blue one, which is peaked, and then a brown one, which is also peaked even a bit more, but shifted to the right. What happens if we apply those 3 priors to the full data set, and we focus again on the BMD? Well, this is again the default priors. We have seen this figure before. How does it change if we go to the next one? You can see how it changes. Now, if you look, and let's focus on the BMD, my prior was very much in line with the data. And it just go together, act hand in hand with the same information almost into a more accurate result. You see here, it goes to 0.4, here it goes to 0.6, it's more focused, okay? So you have a more accurate one. This is what you get if you use the last prior, which is also very informative, but it's shifted to the right. And you see also how the posterior is pushed in the same direction, not fully, because the data say, hey, wait a minute, not that far. I mean, I have also something to say. The data have the most to say, but the prior pushes also. So it's a kind of balance between both. So this is the summary of those together, and you can see that the results get, again, more and more accurate. But of course, if your prior is deviating from your data, you get a kind of shift in that direction. And that shows that also the strength of an informative prior is also something to be very careful with, because you have to be sure that your prior, certainly if it's very informative, can be very well motivated, because it can have quite some impact. This took more than I thought. There's a question slide waiting, but of course we don't fit one model. We fit for quantal data 8 models. Here, all 8 are fitted, and you get 8 credible intervals. You see, one is quite different. Yes, that's because this curve is perfectly fitting those data, but misses this one. We can go into that. There is an explanation for that as well. And at the top, we see what we call the model averaged credible interval. But that's the next part of my presentation. Perhaps there are some questions. If you're still awake, I'm going to get my coffee.
Hi, Mark. My name is Zheng Lei from Bayer Crop Science. In this section, you talk about from historical data to build a prior, informative prior, but there are multiple ways, and you talk about using the PERT distribution. First, I wonder why not directly using the posterior derived from the historical data to used as a prior. And then there are infinite choice of priors just by the PERT distribution. How could I defend my prior choice in front of regulator?
Yeah, thank you. These are very good questions. So first of all, why not just using the posterior? So we can go back to that particular slide, I think, where we start building the. So this is the posterior, right? And then we try to match this PERT on it. Why not using the red curve as well? Well, the problem is we don't have a function for it. We need, in the program, we need to provide a function, a mathematical description, a function. We don't have it for the red curve. It's simulated. So we come to that later on. We don't have an analytical solution always, mostly not, only for very simple cases. There is not a formula for the red curve. We have like 30,000 values of that curve, and the curve you see is a density fit to those 30,000 simulated values. Yeah? So I can give you those 30,000 values, but then you cannot give those 30,000 values as a prior. You have to give formula. Okay? The next one, indeed, is that there are infinitely many distributions you could try to match to it. I can only confirm that. We came to the PERT choice as the implemented choice, mainly based for two reasons. We have done many simulations, mostly with the normal, because in many instances, the normal can be a good approximation for a posterior, but we were not really convinced or happy with, or not always, with the results from that. And gradually we moved to the PERT through its simplicity mainly. And also, I mean, it's not only historical data which might be used for that informative prior. Perhaps you don't have the data anymore, but you have from literature just a confidence interval. Yes, and it says it was a very solid analysis, a very solid study. You will really trust the results from that study, but you only have the lower limit, the estimate, and the upper limit, and that's all you have. So what should you do in that case? Now, the characteristics of the PERT are exactly the min, mode, and max, and the shape parameter to play with also as a kind of sensitivity parameter. And in the simulations, that PERT distribution acted really well. Of course, that's simulations, and that's one. And the simulations we did was not really for constructing priors, more than for looking how priors acted and performed and lead to results you would expect it to lead to. So I think further experience might shed more light on perhaps other choices than the PERT distribution to be implemented as well in the package and to be used as well for a sensitivity analysis. So I can only follow you in the idea that other choices could be made to construct informative priors.
But also, I mean, the fact that it's simple and then other sources of information can be used, like expert knowledge elicitation, for instance, in which you are normally based on minimum and maximum and maybe most likely value. That simplicity basically also was important to select that specific prior as the default prior for our models in order to inform the model. Okay. Whenever we are using the default priors in the approach, these ones are basically still very flat. Those are what we call it weakly informative priors. Okay, in order to be able to just get the model to be stable enough to be useful, and then also to get some results out of it. But it's just mainly because of simplicity, and most of the time we have only very limited information in order to be able to construct those informative priors.
Okay. I think there's time of possibilities for questions later on during coffee break, so I have to push myself. The next basic component is model averaging. Now, this model averaging is not new. I mean, this is part of the exercise already in the previous guidance and the implemented software. So the general idea, the rationale is the same. You want to account for the uncertainty about the model. There's not like, you have to think about all models are wrong, but there might be very good approximations. And so between the approximations which are good, you might have like several models which are equally good but lead to different results. And this is the type of uncertainty you would and need and have to account for. Scientifically honest, you have to account for that uncertainty, and that's what the approach does. Now, I'm not going to spend too much time on this slide. The average, you make an average fit in the previous implementation by just averaging out all fitted models of all candidate models with some weights. And these weights were based on something like AIC, a goodness of fit criterion, which might be difficult to really grasp what it is. There is a rationale for it, and it's okay. I mean, I still support this as well as a frequentist approach. But the Bayesian approach follows the same idea, but is actually again more natural in terms of interpretation. We talked about priors on the parameters. We had the example, the simple example with the background. We had the second example with priors on all of them, with focus on the prior on the BMD. So you have, given the model, you have priors on those model parameters. But you also have priors on the models themselves. So you have, at two levels, you have priors. You have 18 models. They can all have a prior. So indeed, if there is evidence, scientific evidence that the normal distribution is not a good choice, is wrong, you can put those priors on 0. And it doesn't play a role. It's excluded. Because if a prior says it's not possible, no data can change that because it's not possible. Now, those prior on the models are also with the same, essentially the same formula from your course. Who thought that this formula would be so interesting? Turned into posterior model probabilities. And these are the weights. So you start with some knowledge. Do I know something more? Do I know that this model is more appropriate than this model? Do I know that the log normal is more appropriate than the normal? What do I know prior? I can put in the prior. Again, the data play their game, and they change that in posteriors. So the data might say, well, after doing my exercise, those models are not good, that distribution is not so good. These are the weights. And you have your, and now you're mixing the two posteriors. So you have your posterior. Let's focus on the BMD, because in the end we are looking at that. That's a prior turned into a posterior at the level of the parameter. But then these posterior distributions for 16 models are combined with those model posterior rates to one new posterior. Yes? And that's very appealing, because what does it do? For each of the models, you get kind of updated knowledge about the BMD. But some of this knowledge is not trustworthy because it gets a low weight. It's based on a bad fitting model. So it combines all knowledges by putting their weights, which expresses how trustworthy that posterior is, because the model might not be a good model, or might be. And from this new posterior, you look at the 5% lower and upper limit again. As you could expect, at the level of the models, the priors are the uniform distribution by default. So uniform in a discrete way, because you have 16 models, each of them gets probability 1 of 16 in the continuous case. If you say the normal can be discarded because that's for a good reason, they get 0 and the others get 1 over 8. For the quantal, there are only 8, so they get all probability 1 out of 8. Now there is a technical issue that computing these posterior model probabilities is a bit cumbersome, because there are some analytically not so tractable integrals. I don't know whether you had an integral course somewhere years ago, and I think you still remember that there were some integrals which were not so tractable. Now, this is a problem here. So one tries to avoid, you cannot even compute, you cannot analytically express them, so you have to do it in a different way. There are different solutions. We implemented 2 solutions. Okay, if I have to take an integrand of a function that's so difficult, let me try to simplify that function, which is a good approximation, but so that I can deal with it. That's what we call the Laplace approximation. That's fast, but it's an approximation. But it can work very well and can be very stable. But it can also perform a bit less because the approximation is not so good. The other thing is you can compute an integral by simulating values. That's a bit technical. So you can compute that integral by generating many values, and so you can calculate that integral by composing all contributions from all those values. And there an option is bridge sampling because it's very efficient and accurate, proven to be. So these are the two options. Let's now do this exercise on this data set again, the quantal type of data set which we looked before. We looked already at the 8 different curves and the 8 different credible intervals, but now we're going to do the exercise by computing the posterior model weights. That's what you see left below here. You can see that the inverse exponential gets the highest weight, that it fits the best to the models according to the mechanism. These are all the weights. These weights are combined with the posteriors for each of the different models for the BMD, and this is the kind of mixture. So you mix the posteriors for all models for the BMD with those weights, so most contribution of the inverse exponential model, and you get this one. This is with Laplace. What do you get by the other option, that's bridge sampling? Now you might say there are some differences. First of all, you see here that this strange fit is now more aligned with the others. Okay, that's something you could say, right? Here you could say, hey, this looks completely different. No, that's not the case. That's because the scale is different. The scale here is stretched because of this interval. Okay, here it goes from 0 to 5 or something like that. That's the scale which you look at here. So they're more similar than what you think. Yeah, it's just because this one is more alike with the others that the scale is adopted and they all look more alike. And the result, the weights are not so much changing, if you see, and the posterior is changing a bit, but not dramatically. So the Laplace is the quick option also to explore the result. The final result, which should be reported, is based on the bridge sampling. Exercise. Questions?
Thank you. Why did this strange fitting curve disappear in the Bayesian setting?
Well, we should look in detail, but my guess is that in the approximation, Laplace approximation for this particular curve, something went wrong. So I think it's the blue curve, the probit curve. Hard to see, but it's not fitting that bad. I mean, all other curves, as you can see, are not fitting so well at this point compared to that strange fitting curve, right? This as well is perfectly fitting those two, but then it really goes too high in this curve. So the Laplace approach identified the solution for this particular model in this way. It's an approximation that acts for all different models on its own. It's not like one exercise for all models together. So it acts for each of the models, and apparently for this model, but I really would have to look into detail what happened, but that's a bit my guess. And for the bridge sampling, the models behave more or less similar in the way they try to find the solution to fitting the data and approximating the model, the true model. Okay? But we can discuss it later on. You have still points to address this because time runs right. I'm behind schedule already a lot. 10 minutes behind. Ah, okay. Okay. Yeah, but this is the part where I took most of my time for, because I hope at least that it sheds some light on yeah, what's happening inside. Because what's now on is different. So we're looking at those preliminary tests. It's different, but I think it's important. If there are prior views on the data and the distribution, for instance, that's good. I mean, that's nothing wrong with that. But data are data, and so it's always good to check with the data at hand whether there are violations of assumptions about, yeah, which we are applying. So if assumptions are violated, it's difficult to, in general, just say, okay, this has a lot of impact or this has little impact. So the impact of a violation is really specific to the data, to the situation. But at least we can have an alert. So of cautiousness that the results are these, but there was an alert about that assumption. Okay, so that at least this is reported. So what are the preliminary statistical tests? So there are tests for normality and log normality. There is the kind of, call it indirect tests, because the normality assumes constant variance. The log normality assumes constant coefficient of variation. That we can do with summary data and with another test with individual data, depending on the data you have. The third test, which really checks the individual data at a fixed dose, that's only possible for individual data. So this is about assumptions. The other two tests are not as such assumptions, but are also worthwhile, I think, because the first is testing for whether there is any effect. Because, I mean, if it's really no effect, you might already see it, of course, in the data, but it's good to have some confirmation of it. And then you might say, here it stops. Also, as I said, model averaging assumes that at least one of the models fits sufficiently well, given the assumptions. So it might be good to check whether the best fitting model fits sufficiently well. Because if that doesn't fit sufficiently well, you might say, well, you might still have a problem because all models seem not to fit sufficiently well. Okay, quickly, the upper part of the tests, the first button, are frequentist type of models. Tests. They are based on p-values, and I'm sure you all know about p-values. That's in the world of frequentist hypothesis testing. That is not existing in the Bayesian world. P-value doesn't exist here. One uses a Bayes factor, and that's again prior updated to posterior. But let's first look at these p-value type of tests, which are existing. They're not newly developed, so we're just using existing functions in R. The normality assumption, by checking whether it's not really the normality, but it's the behavior of the normality assumption across the dose levels that the variances are constant. So sigma 1 at the first dose is sigma squared n, where n is the largest dose. If you only have summary statistics, you can do this with the Bartlett test. I'm not going to explain the Bartlett test. That's not so important. If you like, I can give you references. The same for the constancy of the coefficient of variation. Full slide, don't bother too much, but you can test for the log normal, the coefficient of variation to be constant with the Bartlett test again. So let's look at this example. So remember, this was a generated, simulated example coming from an exponential model with background 7.5, maximum 15, and a BMD of 0.229 or something like that. Now we have only the summary data. We don't see the individual data. What does the Bartlett test do? Well, the Bartlett test finds a violation against the normal distribution. It says, I have a p-value that's so small that there's something wrong with the homoscedasticity. The normal distribution is violated in its assumption of constant variance. Which is true. I mean, we generate the data with the log normal. And the log normal doesn't seem to have a problem. Bartlett says p-value is 0.4. Don't bother, go on. So we detected evidence against the normal distribution with the Bartlett test. You can do the two tests also with individual data, but then it's the Levene's test, and these are the results of the Levene's test. They are completely in line with the Bartlett test. Bartlett test, summary data, Levene test, individual data. But they identify that there is a problem with the normal distribution. You might decide then, okay, let's kick out the normal distribution. As such, that's not really the idea of a prior, because a prior should be fixed before having seen the data, before having used the data. We are already using the data, but let's see what happens later on. Okay, then we still have the test over here, normality or log normality for individual data. So it checks whether at each dose the normal distribution can be rejected or not, or the log normal. And now we need the individual data, so the bullets. What we find is, based on these data, that there is no evidence against normality at 5% level. There is no evidence against log normality at 5% level. Although we know it's log normally distributed, this test doesn't detect that, sorry. This test doesn't detect it. But that has to do also by power. I mean, you don't have so much data at each dose level. And it does find a problem actually at the highest dose here, but you see these data are, by coincidence, pretty peculiar, like 3 groups. And at 10%, you can reject their normality and log normality. But of course, a frequentist type of test with p-value, you know, there's type 1 error, type 2 error. So 5%, no evidence against none of the 2 distributions, but we already have evidence through the Bartlett test. Okay, then we go to the Bayesian type of testing. Again, priors posterior. So you have a null hypothesis, you have an alternative hypothesis. Here you have prior knowledge about both hypotheses. You can say the odds for the null hypothesis. What is my knowledge about the 2 prior to having seen the data? Suppose I look at no dose effect against there is a dose effect. Do I have a prior belief about it? I could express it. If I put the 2 probabilities equal, then this odds is equal to 1. At the left-hand side, we have again the posterior odds for the null hypothesis after having used the data. And the transformation here, the factor that does this conversion, is the Bayes factor. And that's what's computed and can be used in favor or against one of the hypotheses. It's not based on a level of significance as we are used to in, with p-values. It's a classification that says there is strong, some insufficient evidence in one of the 2 directions. Of course, if this Bayes factor is large, your odds in the null hypothesis will increase. So the larger the Bayes factor, the more it's in favor of the null hypothesis. Okay? Now, using this classification is also a bit complicated, so to say. And how do we use it for our 2 tests? So if the null hypothesis says no dose effect against any dose effect, then we collapse the classification into 2. Only if the evidence is very large for the null hypothesis, we say there is no dose effect and it stops. But we want to leave the door open in all other cases to continue and find out whether this test might have missed something. So this is turned in a dichotomous decision. And if we apply it to this particular data set, well, the base factor is so small, and the smaller, the less it goes in the direction to the null hypothesis, and more in the alternative hypothesis that says there is a dose effect. So here the conclusion is, well, you can formulate it in different ways, but there's insufficient evidence that there is no dose effect. So we continue. Okay? Then there is the other test. There is a best model identified. Is this best model sufficiently fitting? So we compare it to the best possible you can fit, that's a saturated model. The saturated model goes perfectly through the points. Okay? It's overfitting. It's not monotone, but it's just an ultimate contrast with kind of best you can ever do, although it's not monotone. Again, the base factor. And here we go for the saturated model, so saying there is a problem only if the evidence is very strong for that saturated model, because we know that saturated model has advantages which is not, let's say, an honest play. It doesn't have to be monotone, etc. So if you apply it here, so we make it an easier decision on these data set, the base factor is 9.4. So the decision is that the best fitting model which you are looking at is sufficiently fitting well. Questions? No, no questions. Everybody is thinking about this coffee. Okay, let's go to some further illustrations, and this can go fast, I think. We look at, again, this simulated data set. Okay? And what these are the characteristics of this data set. And so the true BMD is 0.228. These are the A, B, C, D parameters, or the natural parameters. Remember the 7.5 and the 15 and the BMD, which we used before. So what are we? This is wrapping up what we already know from the preliminary tests. So we had some evidence against the normal distribution. The best fitting, the gamma fits sufficiently well, and there was evidence that there was a dose effect. So that's summarizing the preliminary tests. But remember, there is evidence against the normal distribution. Now we are looking at the two analyses, whether you use individual or summary data. How do those differ? Okay. Now, first of all, you cannot do some tests with summary data. You cannot do the Shapiro-Willis test, for instance. So that's missing. And the log normal needs the geometric mean and the geometric standard deviation, where you typically have the arithmetic versions. But there are formulas for that. You can compute them, of course, exact from the individual data, or you can approximate it from the arithmetic version, and you can see that's not too bad. Okay? So we don't expect too much of a difference coming from that approximation. Here we see Laplace first row, bridge second row, individual left, summary to the right. The weights for the different models. Hey, what do we see? Well, all normal weights are 0. Remember, we found evidence against the normal weights. We didn't put the normal weights on 0. Yes? The posterior model weights were computed, like for all models, and in some way, so to say, it was punished that there was a problem with the data and the normal distribution. So even if you ignore the warning, and if the data have a problem with an assumption, like the normal distribution, the weights take it into account. They account for it. So that's nice to see, that the weights act with that, like that. Here we have the different credible intervals. I just skipped the normal ones, just to make the plot less busy. But what you see is that the credible intervals vary quite a lot across the different models. So if you would pick one model and somebody else would pick another model, your results could be substantially different. And look at the green top credible interval, that's much wider. And that's what you see, that's the price to pay in some sense, that you account for the model uncertainty, so the interval gets wider. Here are the fitted models for the 4 combinations, and you can see why there are some varying models over there in the area where it happens, because there's not so much data information between the lowest and the first dose. So the models can fit to the data pretty well, but still have a lot of freedom to have their own face in that area. And these are the different posteriors for the BMD, and this is the table across all 4 combinations. After all, if you look at the numbers, you can say they're pretty close. Okay? Right, illustration 2, the other example we have looked at, the fetal weight. Let's analyze them with the BMR of 5%. The preliminary tests, the first test for constant variance and constant coefficient of variation says it rejects both. It rejects the normal distribution and the log normal. Also, the individual data test rejects both. The log normal is rejected and the normal is rejected. There is not rejected at the highest dose levels, but you see you have less data there, which is another issue I don't want to go into. So probably it has not enough power to detect the problem there. So this is more like, let's add another distribution rather than skipping one, because both distributions are rejected by the data. But we have to continue, but it's an alert, and it should be reported that the results are what they are, but there were violations for that assumption. The test for no effect was okay, and the best model fitted sufficiently well. Okay, here you see the weights for the different models. Here you see that the log normal get weight 0, or almost 0. You might say, why is this? Well, if you would look more into those p-values, for instance, the p-values, although they are already so small, also for Shapiro-Wilks here, indicate a larger problem with the log normal than with the normal. And so the weights show that. There is a bigger problem with the log normal than with the normal, so it puts those weights down there. These are the, at the bottom, the model-specific credible intervals. Then you have the different fits, and here below you have the averaged fit across the different 16 different separate fits. Here I show only the normal fits because the log normal got weight 0, and this is the posterior. But there is something, these are the estimates. We'll show them later on again, because I wanted to make a point that there is a problem with this situation, so to say, which we ignored. The data are clustered, or there are litters. So the individual fetal weights are regarding different litters. So there is a cluster effect. You expect the outcome for fetuses from the same litter to be more alike than from different ones. But I think this is so interesting. Okay, I go quicker. At the bottom, just an idea to see the litter sizes. This is just to make the point that the intra-litter correlation has an effect and comes down to an implicit sample size reduction. Results are more alike. Suppose the correlation is 1, then all fetuses in the same litter act all the same, and there's only 1 unit of information. Of course, that's an extreme case, but so you can expect, and this is what we see, that the confidence intervals taking into account the litter structure are wider, because the independent pieces of information are less in number. And that's what you can see also in the posterior. At the right column, you see that this is wider. And this is what you can see also in the final numbers. The correlation was estimated to be 0.5. Illustration 3. This is an example with covariates. There's actually also a litter effect, but that's not considered. So these are the data. So we have male and female. We have the number of days, 21 and 42. So these are two covariates actually, but we can only assign one categorical covariate, but you can then make a combination. So here we have 4 combinations of the two binary covariates. So this would mean that each of the parameters, natural parameters, and also the parameter d and sigma squared could be depending on the covariate. That would mean we have to fit 512 models. That's making too much, taking too much time. So we only fit 4 submodels. One is with background and variance, both depending on the covariate or none of the two. And then the BMD and D, who act together in the formulas, both depend on the covariate or not. So we have 4 combinations, and we fit 4 submodels of each of the models. If there is, then for each of the models, so we have 4 submodels, we identify the best fitting model. And if across all of these models, there is a best model where the BMD depends on the covariate, the result depends on the covariate. If for all best models, the BMD is not depending on the covariate, we get one single common BMD estimate. I'm going to skip this one because they're looking angry to me, as usual. This is the best fitting model in the end, which gets the highest weight. You can see it gets a weight 0.9. It's the Hill model with the log normal distribution, which gets the highest weight. And you see these are the 4 curves for the 4 combinations of gender and the day of measurement. And these are then the BMD estimates. No questions? Last slides. We did a lot of simulations. And I had a number of slides about this as well, but these guys said, no way. So I only have a limited number of slides. This is just saying that it has strengths and weaknesses because you can, of course, compare with the truth. You can look in detail, change one thing and remain everything the same, and you can really get insights. Of course, there are limitations. Your results are limited to the scenarios, and reality is always a bit different. This gives you some information about the scenarios we looked at. In total, 120 scenarios, 1,000 data sets for each scenario. You use the Flemish supercomputer to do that, because if you have to do it on this computer, it takes 10 years. General recommendations, very general, but there is a report which gives you all details. In general, the focus is on the BMD. The background informative prior is less influential, okay? So that's what we saw. We played with different priors, very informative, less informative, not so much of an effect. For the maximum, that prior could or can be very informative, especially in the case when the maximum is not reached yet. If the data are such, the range is not far enough to reach the flattening, the asymptote. And so you might have to put priors on that say, hey, the asymptote is not reached yet, and you can do this in different ways. The BMD informative prior is highly influential, and there we say use the most informative shape parameter only if you are really happy, so to say, convinced that this very informative prior is justified. Okay, we tried out 3 different priors for D. These are optional choices in the package as well. It's good to do a sensitivity analysis there. And yeah, there is also by default an extended range implemented. So we did some simulations there as well, and we consider sensitivity analysis as well for that one. Wow, just in time.
Almost.
Thank you so much, and sorry for taking too much time.
It was just the... That was just the lower confidence interval of the timing, which is usually for academics 15 minutes, and you did very well. Thank you.
Sorry.
So let's have a coffee break. At least I need a coffee now. Let's resume at 16:40, please, sharp. Thank you. Okay, I think we need to restart, and I just give the floor to Bernard Botex.
We wait for a couple
So-
3 minutes.
Okay, so the web streaming is overriding my time schedule because all the people on the web are having...
They are back.
Okay, good. They are back as well. So Bernard Botex is giving you now an introduction of the future, not looking back, but in the future, how EFSA will address benchmark. Future. Bernard, please.
Thanks a lot, Joseph, and welcome back, everybody, also the participants on web stream. So after 1 hour and 35 minutes of mathematics, let's change a little bit the role and let's try to put ourselves in the shoes of a risk assessor who has to deal with the assessment of a substance. And you will have in front of you a number of data sets dealing with various endpoints, and the question is how do you apply in practice this Bayesian model averaging for coming to your health-based guidance value. And if you have looked at the guidance document, you have seen a quite complex decision tree, but I will try to drive you through the various steps slowly. What I want to stress is this blue square, which is referred as problem formulation. And these are a number of issues you need to consider before starting with fitting your models and launching the analysis itself. And you see that it's more than half of the decision tree. So there are quite a number of issues to think of before doing actually the modeling. So there are 4 main issues. First is to look at the data in front of you and decide which of those data or those endpoints are you consider for the modeling aspects. There are 2 different schools. The statisticians will tell you, well, just model everything, and the outcome of the modeling will tell you which is your critical endpoint because of the lowest BMDL. EFSA is more of the view that you use expert knowledge and you may look at the various endpoints and decide those that are potential candidates for deriving the reference point and establishing the health-based guidance value. So you don't necessarily need to model everything. Then you need to have a bit of closer look to your data and you see is there any indication for sex, age group, population characteristic differences or opportunities for merging different data sets. So anticipate the need for covariate analysis. And in the same way, are some of my data linked to possible litter effects that I need to anticipate. And then what was mentioned by Mark, by default, the system will try to model the data with the normal and the log normal distribution assumption. But if you have statistical or biological reasons for rejecting one of the assumptions, you can already think about it, or you might also say, no, and in this case, it's another type of distribution that I want to test, and that's the right moment to think about it. The second aspect to think of is the selection of the BMR. And here we make a difference between the type of data, whether we deal with continuous data or quantal data. And when it comes to continuous data, so it was explained before by Joseph, the BMR is the degree of change that defines the level of response in a specific endpoint that is measurable, considered relevant to humans or to the model species, and that is used for estimated the associated dose, the benchmark dose. And in short, it should reflect a dose where an effect becomes adverse, and therefore it depends on the nature of the endpoint selected. Just to clarify, you don't need necessarily one single value. A level of adversity can be identified can be also a range of BMRs if you are unclear about what is the lowest effect level that you want to use as BMR instead of a single point. And the increase and the decrease or the decrease of the BMR should be a value within the observed range of experimental response. If it falls out of the response range, then you should consider whether the study is able to derive a reference point. One point that is quite important, and this is the last one that is stressed, and this is something that was been agreed during this meeting mentioned by Joseph with WHO, where all those experts were brought together to agree on consensus concepts associated with benchmark dose analysis. If you are not able to provide a biological reasoning associated with the value of the BMR that you are selecting, which if you are not able to say what is a biological relevant critical effect size for the endpoint that you have in front of you, you shall not use this endpoint to derive your health-based guidance value. You can use it for other purposes. You can do some sensitivity analysis, pick number of BMRs, look at the corresponding benchmark dose, and what is the margin of exposure compared to those values. But you cannot base your health-based guidance value on this endpoint because you are not able to say what is a biologically relevant effect. This is in line with what is described in Chapter 5 of EHC 240, and this has been implemented in our guidance document. When it comes to quantal data, it's a bit simpler. The BMR is defined, again, it's in terms of an increase of the incidence compared to the background incidence. And here we go to a BMR of 10% because it's the lowest statistically significant increase in incidence that can be measured in most of the animal studies. And normally, it should not require it should require little or no extrapolation outside of the observed experimental data. So here we are a bit more relaxed. If you go with a 10% BMR, we are fine. And any decision to deviate from this proposal should be explained and presented your assessment. The third aspect is the suitability of modeling, of the data set for modeling. And here, there are different cases. If you look at your data set, and if you are able to identify 3 different dose groups, so this is the figure on the left, dose group does not mean dose. So dose group is doses with the similar type of response. Then you see the green tick, so no problem here. You will be, it means that you have enough information on the dose response with this data set, and you will be able to perform the modeling, and you will get potentially useful benchmark dose and benchmark dose confidence in a credible interval. In the same way, if you look at the right figure, which means you have only 2 dose groups, but here you have plenty of information, the lowest dose range, which is where you expect normally your benchmark dose to be. Even if you have a gap with the maximum response, you will still be able to get a useful benchmark dose and a useful BMDL out of the modeling. The problem comes with the figure in the middle, where there is a gap in the study design, and they have forgot to put some doses in the area of interest. And this will result in, you can expect at least that it will result in a very low BMDL and a very wide benchmark dose credible interval. And you will notice that the X is not, could have put it red, but we put it yellow because we are not saying that you should not model. But you should expect that the outcome of your modeling from a risk assessor point of view will be of problematic use. Let's word it like this. Okay? So it's not stopping you from modeling from the modeling it, but it's to alert you that you will expect some huge uncertainty around your reference point associated with this type of data set. If the data are not showing any dose response effect, the new guidance document is reintroducing the possibility to consider whether the NOAEL or LOAEL approach is applicable. I will come back on this because there are still some aspects to consider if you go back to the NOAEL-LOAEL approach. The new guidance is also clarifying a number of issues we had in the past in the application of the previous guidance about the high dose impact. So when there is the issue then when the high dose data are available for the effect of interest, but the high dose point is clearly influenced by another type of effect or mode of action. The question is, when do I decide to exclude a data point from my modeling, or when can I do it, when can I not do it? The answer, the clarification put in the guidance is, if I'm able to explain biologically that there is a new type of toxicity overlying, or there is a different mode of action entering into play at high dose, that can be a reason for excluding the data point. But if you have no such explication, or if you have no indication of such overlying mode of action, you should not remove your outlier from the modeling, because you have no biological reason for doing it. Then the maximum response is quite impacting the BMDL and the benchmark dose credible interval. So in those cases where at the maximum response you have not reached the plateau yet, then it makes sense to, and that's the added value of the Bayesian paradigm, the Bayesian approach, to see if you have prior information, historical information that tells you around which value your maximum response should be, because it will reduce the lack of information in this area. Last point, obviously, decision to exclude one or several points should always be justified and documented, and the sensitivity analysis should be provided considering the observation included or excluded. So this is for somebody who would like to reproduce your assessment, your analysis, to understand what you did and the consequences. Then comes the issue of non-exposed controls, and this is a tricky one. There are cases where there is no zero dose, meaning you have always a background exposure to a substance. Or if you think in the area of nutrition and nutrients that are necessary for you to be in good health, there is no absence of exposure to those nutrients. And this is something that is to be taken into account when you do the modeling. So if the dose response function is flat at the lower dose range, there is no uncertainty in the extrapolation from your lowest dose, the background exposure, where you have a certain amount of exposure to your compound, to the zero exposure. So that's fine. The problem is if you have not reached this horizontal line close to the zero dose, and in this case, the steeper the curve will be, the higher uncertainty you will get in the extrapolation to the zero dose. So how do you deal with this situation? Here we are on a case-by-case approach. Can make assumption on the expected value of the outcome under consideration at zero exposure. So there are priors, you can have knowledge elicitation, that was mentioned before. And it will become even more complicated when you consider nutrients where, let's say, a certain level of exposure is necessary to remain healthy, But then the toxicity is arriving also very close, and there is kind of uncertainty around the two values, because it may end up with the BMDL falling below the actually requirement for LC, for the people to be in good health. So this is something for which we have little experience so far, and we go on a case-by-case approach, meaning Joseph in the previous guidance was referring to this orange box where there was written consult a specialist, and this is still the recommendation. When you are in this type of situations, if you are an EFSA expert or dealing with an EFSA assessment, there is a standing working group on benchmark dose, will help you managing this type of situations. If you are out of EFSA, the recommendation is to consider to consult a specialist in benchmark dose response modeling to figure out how to deal with this type of situations. And the more experience we accumulate with this type of situations, then in the future we will consider if we can provide additional guidance to deal with those situations. About the prior information, I think Mark was quite extensive, so I will not spend too much time on this aspect. Let's say that, we are interested in whether we are able to get prior information on the background maximum minimum response and the benchmark dose, as it was indicated, and using the PERT distribution system, so it's translated into the minimum and the maximum and the mode for these values. So once again, the story of prior information, you realize we are still in the problem formulation. We are not in the post-modeling aspect. So if you need to make the effort to identify whether such prior information will be needed or is available before you do any type of model. This is something quite important. Now we have reached the end of the problem formulation. So you have realized that there is quite a lot of things to think of before actually going with the modeling. Then you go with the modeling, and you will get, so that's quite easy, you put we'll see the platform tomorrow, and Jose is going to introduce it. You push the button, fit the models, it will do all the calculations about whether the assumptions are met or not met, etc. And it will provide you with an outcome of the analysis, which is the average model benchmark dose and credible interval. And the question that will come to you is whether the result is suitable to be used for defining for deriving the reference point and calculating my health-based guidance value. The first thing I want to stress, and that's why I mentioned the importance of identifying the eventual use of prior information at the problem formulation step, that you don't do post hoc modification of the parameters after you have got the results of the modeling. I mean, you don't realize that you don't like, to say it in very crude language, I don't like the outcome of the modeling, I'm going to consider changing some of the parameters. Why not increasing the BMR? Why not, maybe I could put some prior information on my background. That's too late, because it could be interpreted as playing with the data just to be nice. So this needs to be done before. Then, it was not clear with the previous version of the guidance document, what are the criteria for rejecting or considering the outcome of the modeling as not relevant or not suitable for the purpose of my assessment. So we try to give a number of criteria that you see on screen, and those criteria are inspired, let's say, on criteria proposed by the US EPA in their guidance document as well. and you see them on the box. So none of the candidate model fit the data sufficiently well. There is the ratio between the benchmark dose and the benchmark dose, the lower confidence band greater than 20, or the BMD is 10 times lower than the lowest non-zero dose, or the ratio BMDU, BMDL is greater than 50. Here we put a little aparté. Those values, they come out of nowhere, meaning they have been suggested by US EPA, reconsidered by EFSA. I say, okay, these are possible thresholds. Let's try to apply them and see if they work well, if they need to be revised. So they are not written in stone, and based on accumulated experience, they may be reconsidered in the future, but that's a starting point, because we had to give some criteria to decide when to eventually reconsider the use of the outcome of the modeling. If you don't match, if you don't fit with one of these criteria, there is no reason for excluding the outcome of the modeling, and you need to consider it for your assessment, whether you like it or not. Okay? Now, if you fall in those criteria, we are not recommending to jump directly to the NOAEL. There is an intermediate step that you see, it's point 1, which is to use the probability distribution of the benchmark dose. That's an added value, the Bayesian approach. You get the probability distribution around the benchmark dose. And you compare the most likely benchmark dose of your posterior distribution with the various experimental doses that have been tested in your data set. If the most likely BMD is lower than the NOAEL or the LOAEL, since you put yourself in the conservative approach, you will consider the most likely benchmark dose as reference point. If the most likely benchmark dose is greater than the NOAEL LOAEL, then it makes sense to consider the NOAEL LOAEL as reference point. You see the third bullet, which remains one of key criteria, the key criteria. The most likely benchmark dose should not be lower than 10 times the lowest non-zero dose. If it's the case, don't consider this. In any case, and if the data are considered not suitable for the benchmark dose modeling and the use of the most likely benchmark dose is considered unreliable, the last option is to use the NOAEL. But whether you use the most likely benchmark dose or the NOAEL, you still report it with the credible interval, so that the risk manager gets an idea about the uncertainty associated with the reference point that you bring into him and out of which your S-based guidance is calculated. So no NOAEL in isolation, we want to see the NOAEL plus the credible interval that would have been linked to the benchmark dose calculated with instead of the NOAEL. Oops, the computer closed. The next step, so you will do your benchmark dose analysis for the various endpoints that you consider as potential critical endpoints for your substance. The question is which is the overall reference point I want to use for deriving my S-based guidance value. In the past, or at least if you do it purely mathematically, you will say, let's go for the lowest BMDL. Here again, we put a little bemol, meaning that there will be some cases where actually you can deviate from this approach and consider alternative solution. The first case is if the health-based guidance value based on the BMDL with a wide credible interval, but is still much higher than the exposure estimate, or the MOE is much larger than the minimal value considered necessary, then the fact that there is a high uncertainty, you don't really care because your exposure is far away from your reference point or your S-based guidance value. And so you may consider a reference point from another data set that is less uncertain, a bit higher, and that is more practical in terms of risk management implementation. But keep in mind that the exposure you consider at a given moment in time may change in the future, so it's a bit of a risky approach. The second case is if the lowest BMDL concerns an effect that is linked to other endpoints that resulted in much smaller credible interval, but with higher BMDLs. Okay, so this is the scenario 1 and 2 that you see on screen. You have two endpoints that are related. So you take serum enzyme with liver necrosis or relative liver weight with body weight. So endpoint A, in the column endpoint A, correspond to the one with the big credible interval, and the B is the one with the smaller credible interval. So even if serum enzyme is, for example, would lead to the lowest BMDL because it can be correlated or a marker for the liver necrosis, you may say, and I prefer to use the endpoint which is more relevant, and with the lowest credible interval, and I would go for the BMDL B in this case, even if it's not the lowest one. Same reasoning if I'm dealing with two endpoints that have different level of severity. For example, one is about body weight, the second about nephrotoxicity or serum enzyme versus neurotoxicity. I will give the priority to the nephrotoxicity or to the neurotoxicity, even if it's not the endpoint leading to the smallest, the lowest BMDL. So these are the cases, examples of cases where you're not necessarily, you need to make use of your expert judgment and just not necessarily go for the lowest BMDL. Last point, if you perform benchmark dose analysis, this is nothing new compared to the previous version of the guidance document. There is a number of information that you need to report back so that somebody looking at your assessment is able to understand what you did, the assumptions behind your assessment, and to reproduce actually your analysis. So summary table of the data for the endpoints for which the benchmark dose analysis is reported, the value of the BMR chosen, the biological rationale for the BMR values, the software used and the version number, the statistical assumption and settings, if different from the default ones, the table presenting the model used, the benchmark dose estimates, and the benchmark dose credible interval for each of the endpoints, the plots of the fitted model, and the conclusion regarding the selection, the selected BMDL to be used as a reference point. And the good news is that for most of these points, the template has been automatically generated by the benchmark dose application of EFSA that Jose is going to introduce in a couple of minutes. So you need to focus on the explanations on the results. So what is the biological rationale behind the BMR selected, or the conclusion on my final reference point if you don't go for the lowest BMDL, etc. And I think that's all I wanted to introduce very quickly. We should be back on time now.
Thank you, Bernard. Are there any questions to Bernard?
Thanks for your presentation. So my first question regarding the testing of the suitability of the data set. So we have the opinion that, for instance, if you have a data set, you want to check how good the quality is, you can just run the BMD analysis. You derive the BMD together with the confidence interval, and you see how large the confidence interval is, and that already tell you enough. So my first question is, what is the added value of introducing different procedures with different scenarios just to test the suitability of this data set? What is the added value?
Well, we implement this procedure in the case that you would like to just test many endpoints, and you would not be looking at all the endpoints in order to do the BMD analysis. If you have many endpoints, imagine that you have 100 endpoints that you would like to analyze. You might want to have a procedure that beforehand just help you to see how useful is going to be the analysis that you're going to perform. It's not a stopping rule. It basically says there in the application that it's not a stopping rule. It's just to flag that probably your analysis is not going to be useful later on. It's not a stopping rule, okay? Yeah. And in fact, you are able to do that. The application allows you to do all this and just give you this extra information for you to know that maybe the results are not useful, but also showing you why it's not useful, okay?
Ron?
Thank you. Ron Hogeboom, I'm a member of the Contam panel. I'm a bit worried about this BMR issue for continuous data, because I think in many cases it's not so clear if a 5% or a 10% or maybe a 20% would be relevant as an adverse endpoint. And I'm a bit worried that people may easily say, okay, then 1% is the default, becomes the default, and you show that a BMDL5 is more related to a NOAEL then. So I'm worried about this issue that we actually in many cases don't know at what percentage something really becomes adverse and should be called adverse. We're looking at the adverse endpoint, so is 1% enough, or should it be 5 or 10? Is a 1% decrease in body weight? I would be worried if my child gets a 1% decrease in body weight. So you easily end up with the lowest BMR that you can think of. On the other hand, maybe the modeling fails then. That may be the other option. But so I don't know how to do that, and that we should then not use that endpoint anymore if we don't know what is at first.
So the concept is that before we were saying use 5%, you can use 5% as default for continuous data. But the idea is that when it comes to continuous data, your critical effect size is endpoint specific. So you cannot come with one standard default. This has been, and we had plenty of cases where we were going back to the panel and say, why did you use 5% for this endpoint? Because it was written in the guidance document that we should use 5% of default. If you go outside and you need to defend your health-based guidance and say, on which basis did you calculate it? I mean, because the scientific committee told me 5%. It's a bit weak. I mean, so that's why the benchmark those experts because this discussion really took place at this WHO meeting where we are all together. I say, we cannot come with a default value. You need to be able to justify the critical, the reference point, or the BMR, or the critical effect size that you are using for your endpoint, out of which you pretend to establish an health-based guidance value. If you are not able to say what is biologically relevant for that endpoint, how can you defend the health-based guidance value that you will calculate out of it? If you don't know what is become adverse, why is this value and not one? Why not another one? That's the issue. And once again, we don't expect you to come with one single BMR values. If you are not clear what is the critical effect size, you can come with a range, or do an expert knowledge elicitation. Again, we expect the critical effect to appear from this value to this value. Then you do your modeling, you see the resulting BMDL, and you will come with, at least you can explain the rationale behind it.
And as I said earlier on, it's not really a modeling issue. It's really an issue for the toxicologists to agree what is a biologically relevant effect. And also in the WHO meeting, it became clear if you cannot come up with such a value, you shouldn't use that value as a reference point. And as EFSA said already earlier on, you can model any endpoint, and that way, the more the benchmark dose approach is applied to all kind of data, the more sensitive the toxicological methods become, the more of these problems we will see. If you see a slight variation in the T17 helper cell, you can model that, but what would be a BMR which is biologically relevant? And just to stop that kind of discussion, I would like to announce that EFSA is in the process of establishing another working group dealing with how to tackle the issue of biomarkers of effect. The old one with body weight was just an empirical one because in the past 5% was about the range which was experimentally accessible. And that was general agreement. But if you start, is 6 or 7% decrement of body weight, is that important, or is it 3 or 4? That's leading to nowhere. I think this is something outside this meeting, but I agree it's an important point. There is one more last.
Yeah,
First one was the one behind.
Yeah.
Thanks. So, Carsten Kneuer, German Federal Institute for Risk Assessment. That's complicated. Personally, I think one of the intrinsic limitations of the benchmark dose modeling approach is that we're looking at one parameter, whereas usually in toxicology we are looking for patterns. We're not looking at one parameter only, but defining adversity as a collection of changes on different, unrelated, usually related parameters. And that's also where I see a problem with setting benchmark ratios. Now, I'm also grateful that you put up the slide, how to integrate BMD values for different parameters. So my question is related to that. In practice, we often have a situation, as you showed, that we can calculate benchmark doses only for some parameters, but not for all. And how to deal with such a situation where you had the example, liver necrosis, you had liver enzyme changes, but I wouldn't be surprised if we are not able to calculate the benchmark dose for liver hypertrophy or droplet formation, something like that. In that case, I personally would like to also integrate a NOAEL or LOEL value with benchmark dose values. How do you feel about this? How do you feel about integrating NOAELs and BMDLs in that slide where you look at different parameters?
If you have a NOAEL value, it must be based on a data set. The question is whether you're able to retrieve the data set out of which this NOAEL value was used, and then you can redo the analysis and see what would be the BMDL and the credible interval. So I don't see... I understood correctly your question, but I'm not sure. You're saying there is already an established NOAEL for one of the endpoints that is not part of the endpoints that I'm modeling, and I want to integrate that with the benchmark dose that for the endpoints that I'm considering. So
I agree. Sometimes it may be really difficult, especially as you were saying, sometimes you are looking on a pattern rather than on an individual parameter. If you have an isolated increase in liver enzyme without any pathological changes in the liver, then you start wondering whether this is the right endpoint. But let me stress again, this is outside those response modeling. It's sort of how you integrate the data. You can model all endpoints, but whether this is meaningful or not, that's another story. And the more, as I said, the more sensitive endpoints you are modeling, the more complicated the picture will get. And then it comes back to, I'm proud being a toxicologist, so we are not getting replaced by José's model, I can assure you, because it will always be some brains needing to look into the data and saying, well, this is meaningful. And yes, there are situations where possibly modeling is a non-issue because it cannot be modeled. Just think of bulking agents. You will have no effects up to the highest dose tested. Then you are back to the point where you say, well, okay, I have this margin of exposure, I guess it's fine. You don't need the modeling. The modeling is a tool which helps us to better quantify the uncertainty. This is the core issue all about that we want to know how firm the conclusions we draw are, to signal this to the risk manager. And if you are not able to do that, then you should say so. Say, okay, look, I don't see anything at this dose level, but if you model it, you get this kind of impression that it could be there or there, meaning that you are dealing with rather uninformative data sets. And that's the problem. And you cannot replace uninformative data sets by any tool. It may be the situation, especially in the contaminants area, that you cannot go back to someone saying, hey, produce some more data on this compound in potatoes. You will not see any data coming up from farmers. So this is the problem. The other thing is, if you do a good guideline studies, the dose selection may be such that modeling is just telling you that you did the wrong selection of the data, the doses. But modeling is not saying, helping it to make better data. It's just meant to quantify and qualify the data. And yes, you may, in certain circumstances, if you don't have another choice, go back and saying, okay, I'm looking at the totality of the data, and if I had to say something, I choose this effect level or no effect level. So this is what I mean when I say this is part of integrative way in looking on the totality of the data, and the benchmark dose modeling, sorry Jose, is just a tool, at least for me.
Let's take the last question quickly because we are running.
Yep, last question was...
You.
Yeah, you.
Yes, Christian Strupp, European Crop Protection Association. I'm following this discussion since many years, and I'm very happy about all the presentations given so far, because I think what comes out clearly, based on all I heard, is that this is a modeling tool, and the beauty of it only shines out when the data set underlying is appropriate for the modeling, right? Based on the last presentation, I'm a little bit worried about the scenario which had a little green tick on the right side on slide number 10, which was essentially only the high dose shows effects. Yeah, that's great if you could go back to that, because that's how, here, this one, because that's how most of the toxicology studies actually look like, because they are designed this way. Low dose, nothing, mid dose, nothing, top dose, above MTD and jump. I have the feeling that as this seems to be accepted, the maths is not giving us benefit, right? If there is no dose response inside, there's no gain by doing a BMD model versus a NOAEL approach. And I'm just worried that the mathematics are kicking us just artificially into issues. I'm wondering, is there a plan to define a little bit more guidance when you can actually say that this is not a suitable scenario? Because I do see there is some... If you can justify it, it's fine, but this is not guidance. If you can justify it, there will always be arguments for and against. No? Yes.
I had the very same impression when I saw that for the first time. The issue is that the distance between the third dose there and the highest dose is rather small. The problem comes if you have no information from the control up to the highest dose. So then you have any curve between 0 and your first dose. If you have mid-dose, some effects, or even if no effect, then you know your interval where something happens is very small. But Jose may explain it better.
Yes, and I'm happy to wait for your presentation then, because that's an interesting part. I think that's going to be 90% of the cases.
But the issue is that we are not ruling out anything. It's basically just giving you extra information about your data, you know. you know, in general, these kind of cases can still provide informative BMD values, okay? It doesn't mean that it's all the time, okay? It depends on the setting, okay? In general, it gives you informative BMDs and credible intervals that are useful. That's all. It's just an extra added value that we are providing in the tool that I am going to present, if someone let me.
I let you. I think we need to move on, and just to announce that I feel if questions like that come up, it's important to address them. So we will have, in the plan, was half an hour for general discussion, but I think it's also important to link it directly to the presentation. So we may shorten then the general discussion a bit. Jose, please, about the web application of EFSA.
Let me try to wrap up a little bit the things that we have seen until now. I mean, what we have done is just try to put all these things that was explained until now in an application that is going to help you to just perform your BMD analysis, okay? EFSA has a repository of tools that we created. We call it the R4EU, yeah? And it's freely available to everyone that can register. They need to register, but it's freely available. Okay, this is the site in which you can just go there. There are a number of tools. BMD is one of them. It's not the only one. There are other tools as well for other type of analysis. But BMD is, up to date, the most used one, okay? That's why we are very proud of the BMD tool within this repository. And then the registration process is very simple. You just click on the sign up now there, and then this window is open. You just need to just basically provide an email, a password, and confirming that password. Just give information about your name and the country. That's all. Once you just enter that information, you create your account, and then you are able to access all the tools that are there in the specific repository. This is just a screenshot of some of the tools that are there. It's not the only one. You see that there are now 2 BMD applications, the past and the future. The BMD based on the PROAS, still we are going to leave it there. There are some settings that we have no program with the Bayesian BMD analysis, but just to let you know, there are other tools. You see there is also other tools for other purposes as well. Also, performing an expert knowledge elicitation can be done using a tool that we have developed and hosted in this specific site. Thus, the tool is going to look like this. Thus, it looks very similar to the previous tool that was there. Okay, I am just going to show later an example just to illustrate how the tool works. It's going to be a live demo. Thus, if something goes wrong, that's Murphy's law. It's normal. There's no problem. We will deal with it. Well, we are just going to look at specific examples that we will also use tomorrow in the practical session. There's here we are looking at a 28 days oral study. There were a dosing scheme with these specific doses. They have 6 animals per dose, and they were measuring just female ovary weight. This is the data, how it looks like. This is basically just the table of the data with the mean and the standard deviation. If you would have the individual data, which I had, then you could build this kind of box plots for each of the different doses. This is the representation of the data. And this is how you will see it in the application. Now, I need to move towards here. I hope it allowed me to, bad request, that's very nice. Just because it was there frozen. Okay? There's this was the screen that we showed before in the PowerPoint presentation. And does it look very similar to the previous one? You see that the previous one, there was a data tab, a fit model, and some advanced plotting. It's the same kind of a structure as it was in the BMD that was based on PROAS. Here, there is also the possibility to browse and then just go to your data. I will just upload the data that I was just presenting before. This is the data. The features in this tool is different from the previous one because right now we are just dealing with a different method, okay? It's a different approach, there are more options. In this case, the first page in the data is similar to the previous one, okay? Here you need to just select which one is the column in your table that contain the response that you want to analyze. In this case, is the mean absolute overweight, okay? And then you need to define what is the type of response that you have. Then here we have, this is the type of response that we are able to analyze with this tool. Quantal data, summary data for continuous data, or individual continuous data, okay? In the case that is quantal that is individual, then it's basically you can summarize it because you can make a frequency table anyway. I think that that's why we didn't put that option. Okay, in this case, it's a continuous summary data. This is the default option. We can just leave it there, and then we can pass to the fitting model tabs. In here, you can see that there are already some differences, okay? Because you see that in the right-hand side of the screen, there are more information that is needed in order to be able to apply this methodological framework. Okay, but the first part, the part in the left, is very similar to the one that we were having before. You have the independent variable, which is the dose that was administered, and if the variable name contains the string dose, it will recognize it and we put it there, just to try to facilitate the work of the user. The variation statistic. If the string in the name of the variable contains the word SD, it also pre-fill it. I mean, sometimes it's not the right one, thus you need to just use the right column that is basically associated to the variation statistic. Also, if the sample size column would have the name size, it will also put it here. That's why I put N here, just to know. No being selected automatically. Now, you see that this is basically now the same thing as it was before. If we would have covariates, then we could also select the covariates column. I mean, the column that contains the covariate name, okay, the different groupings. In the right-hand side, you have then the value of the critical effect size or the benchmark response. The default is 0.05. You can change it, in this case I'm going to use 10% instead. The probability for the credible interval as it was for the frequencies is a 90% credible interval. The other one was a 90% confidence interval. This is the default value. And then you can use prior information that should have been just gather that information before you're doing this analysis, okay? Like Bernard was saying before. In the case that there is no any prior information that you would gather before you are doing the analysis, the default priors are the non-informative prior or weakly informative prior. There are prior for the parameter D, which is a very complicated one, that need to have some information. In another case, the model becomes unstable. We are using a similar prior to the one that is using a USCPA, but a bit more, less informative, more flat. Okay. There is a possibility also to click or unclick which distribution I want to use. If I want to use only the normal, I can just unclick the log normal distribution. In the case that I want to use only the log normal, I can use only the log normal distribution, meaning that all the weights for the models that are considering the normal distribution are going to be set to 0, because they are not going to be used. Okay. In this case, the model are going to be done only with the log normal assumption. But for that, you need to have a good justification why you would like to use only the log normal models. Because the default assumption is basically that you use the 2 distribution. That's why they are on tick. They are tick. And then we have seen that there are some preliminary tests, to see if there is constancy of variance or if there is a constancy of coefficient of variation. In this case, in which that assumptions are not fulfilled, in the guidance we also propose to perform a sensitivity analysis. The sensitivity analysis that we propose is to use then the smallest variance and the maximum variance observed in the data, and to use that for all the different dose groups, and to see what is the impact on the results of the benchmark dose analysis that you get at the end. How variable it is, the BMDLs that you are getting from those analyses. If they are on the same range of comparable, then, the assumption of homosedasticity that was just basically mentioned by Mark before, this word that is very difficult, then it's basically not that important, okay? Now, before you can run any analysis, you need to see if there is or not a dose response, okay? This can take a little bit of time, but before that, you see there is an option there to visualize if the data is suitable or not. Okay, this suitability test that we have mentioned, it doesn't prevent you from running the analysis, it just gives you extra information. It basically says that there seems to be enough information to estimate the BMD with certain level of accuracy, and you can get also a box plot of the data. It gives you some extra information, and thus it tells you basically there seems to be already a response at the higher dose, for instance, in this specific case. It basically just gives you extra information. It doesn't prevent you from running the analysis. Let us run the dose response analysis. Thus, before you are able to fit the model, you need to click on this. Thus, it means that now you are only going to be able to fit the benchmark dose models if you observe or not a dose response. Because, that was one of the stopping rules in the diagram and the flow chart that was presented by Bernard. If there is no dose response, there is no point to run a dose response model, okay? Okay, now it says that for the two scales, there seems to be enough response to be able to model it doing a dose response analysis, yeah? But before we do that, I'm going to go to the advanced settings, because these are all the features that we have in the application. You remember that Mark, I hope that you remember, Mark mentioned, it took 150 slides, that's it. You remember that Mark was saying that there were two methods that you could use to analyze the data. The Laplace approximation is the fast one. Okay, this is what you are going to use to explore your data. You can use this very fast, it runs very quickly. The other one is the bridge sampling. It takes a bit more time. Of course, not comparable with what it was taking before, because the other one was a bootstrapping. Also remember here, we are running much more iterations than we were running with the bootstrap. Okay, this is also important to mention. In this case, the Laplace approximation is the default assumption because it's the fastest one. But in any results that will be reported, what we recommend is that you use the bridge sampling, okay? Because it's the most accurate method. Laplace approximation is an approximation, okay? Thus, there is a possibility to choose between that. There is a possibility also to extend the dose range for the benchmark dose. The prior distribution for the benchmark dose, if you wanted to extend it, just go beyond the dose tested, okay? In that case, we have put it as the default that is always extended, okay? We say, we think that the BMD might be even outside the range of those tested. That make it even less informative, okay? And we have chosen this because we don't know where it really is. I am assuming that the user doesn't know neither. Thus, in general, this is the default assumption. Thus, the other thing that we have put here in this, the other feature is that now you can select any of the models that you want to fit. If you have beforehand any evidence that the models that we are just basically proposing are not relevant for my problem, you can untick them, okay? And meaning that these models are not going to be used. Because we are giving you all flexibility. The default assumption is that all models are used, but we are giving you all the flexibility that you can choose based on scientific evidence, something that is not the default, okay? Okay, I will leave it in the default, and I will just run the model. Thus, once you click on the fit of the models, then you can also ask the application to send the results to your email address. This was also an option that we were having before. Okay, I'm not going to send me anything. I'm just going to start with the analysis. And then you see that now all of the models are going to be fitting. Okay, and then you see the progress bar of the fitted models. Yeah? Okay, the model with the Laplace approximation already finished. Does it mean you see how fast the results are obtained? You can see here now the different preliminary tests that Mark was just presenting before the coffee break. You can see the Bartlett test. You can see that for this specific case, the two scales, I mean original or log, or normal or log normal, are basically met. The two assumptions of homoscedasticity in terms of normal or constancy of coefficient of variation are met for this specific data set. We see now the different credible interval for each of the different 16 models that were fitted, and the model average, which is in green. And then you see a table as well that basically gives you then the results of the model averaging for the 16 models using the Laplace approximation. You see also that as well a message just indicating if the best fitting model fits sufficiently well or not. That was one of the preliminary tests that we were just mentioning before. It was also one of the criteria that Bernard was mentioning in terms of considering if the model is appropriate or not, or if the results of the models can be considered appropriate or not. Then you see the weights. You have seen this graph already. I mean, graphs similar to this one that were the ones that were presented by Mark. You see that, for instance, now the log normal models are getting higher weights than the normal models. You could also see it as well if you look at the Bartlett test. You could see that for the log scale, the p-value was much larger than for the normal one. Thus, this is also reflected as well in the weights of the different models. And you have a table with every model, the credible interval, and the weight that they receive. Yeah, as well, you get the different graphical outputs of the model fitted. You can see, for instance, that this model is not fitting well, the quadratic exponential. I mean, it's fitting worse with respect to the other ones. You can see it also that the quadratic exponential in general get smaller weight also because it's basically having a worse fit than the other one. You can see for the normal distribution assumption and for the log normal distribution assumption, and then you see as well all of them together. Yeah, these are all the different models, the 16 ones, and then the model averaging one. You see in the model averaging, you see then now the posterior distribution, which is this orange-like curve there, and the credible interval with the green one, and the model averaging, which is just represented by this black line. The good thing of this is that all this can now be as well downloaded in a report as it was before for the previous tool. Because in that case, nothing has changed. Now you have a Word document that I am not going to open it because here there is no licensing for this. You saw it with PowerPoint. But the report contains all the information that just Bernard mentioned before. As you see, the tool is very intuitive in terms of the things that need to be done. There are more options because you need extra options in this specific framework. And on top of that, we got a problem. Yeah, I click on something. Okay. You know, it should not have done that. I can just fit it again, just because my results were basically clean because I click on a specific thing without noticing. I will run it again, this is fast enough, this is not a problem. But once you get the results of your fitting model, then you can also have plots of the posterior and prior distribution for each of the different parameters. Okay, and that is given in the advanced plotting. Okay? You can select the model that you would like to see, the posterior and the prior distribution for each of the models. And this, for instance, is giving the exponential and the inverse exponential. You can see these plots were also the plots that Mark was showing before. You can see for the background response, this is the prior distribution, the blue one, and then the posterior distribution based on the data. Similar for the parameter D, BMD, and the maximum change, the fold change. Thus, you see that for each of the specific models, that you are able also as well to produce results in terms of the prior and posterior distribution for each of the parameters in the model. I hope it's intuitive enough and clear enough to be able to use it tomorrow. Yes, okay, sorry. There was an option I didn't show it. I mentioned it, but I didn't show it. It was the fact that we can just also introduce informative prior, okay? In the prior specification, the default is not informative. You saw the results with the non-informative prior. And if you click on the informative prior, then you get the non-informative prior parameters, okay? These are the non-informative prior parameters for the data that you are analyzing. You can see, for instance, that the BMD, as we selected the extended ranges, is basically the maximum of the BMD is much larger than the dose that was tested. That was 1,000 was the dose, and now we have 1,000,000, okay, because it was 1,000 square. Okay, that's the standard ranges, because we don't have any idea about this. We can then now incorporate some knowledge here in this specific option. If you want, if you would like, I mean, if you know something beforehand, before you conduct the analysis, that the background response should be somewhere in between 0.10 and 0.15, okay? Just now you can incorporate that information. You see that now I put a minimum, a maximum, and a most likely value, okay? The application works with that specific configuration. If you don't have the most likely value, you can also use it as well with the minimum and the maximum value. Okay, you can incorporate this extra knowledge in the application by using the appropriate values for each of the different parameters. Here you see that there is prior distributions that can be defined for the background, which is just the background response, for the BMD, and for the maximum or minimum response, okay? If it is decreasing, it's not a maximum, it's the minimum response. Okay, you give prior distribution for those three natural parameters, as Mark was mentioning, and for the technical parameter, we only provide two choices for the parameter D. The EFSA default is a bit, how do you say, less informative prior for this parameter D. And we have also as well included the prior that is used in the BMDS application from US EPA. Thus, we have also that option as well. The option of the US EPA is a bit more restrictive. It basically just gives 5% probability that that parameter is smaller than 1. Okay, in the specific case of the EFSA, the one that we use as a default, we give 15% probability to be below the value of 1. Value 1 was the constraint that was done before when we were using the frequentis approach. And now we are just basically just giving now a prior distribution to this parameter that has still certain probability to be below that specific threshold. Okay? And I think that that's enough to show all the features.
Thank you, Jose.
Sorry? The report has been downloaded, hopefully.
Yes, and that gives me the opportunity to make a plea. As you have seen, this tool has now a lot of different options you can select. And I strongly urge you, if you use that tool, download the report, because there you will see what you actually have done. Because I'm sure if you want to repeat yourself your analysis 2 weeks later, you might not remember what you have ticked. And then you can see that in the report. And each time you are deviating from the report, from the defaults, you are asked to give a rationale why you are deviating from the default settings. If you use 50 or 0.50 as your critical effect size or BMR, then you are asked, please, you deviated from the default, or what? Well, the BMR default is not a good, that's for quantal. Yeah, let's take quantal, then it's an option. Then you need to give the rationale why you think 50 is the right value. And then someone outside can reproduce that, and then it's a matter whether you agree or disagree on that selection. It's not, again, it's not a matter of the modeling, it's a matter of how you approach and how you use that data. And equally, if you set priors, you should, as Bernard was saying, do that on beforehand. Now the report is there.
Yeah, well, I show what is the report, how does the report looks like. Basically, there is a data description, and just it says that you should give some description of your data, and it contains the table. Then the software used, which is this specific software, the version is there. Then it gives you some information about the assumptions in terms of homosedasticity and for the log normal, the constancy of variance, and there is some information. Then in this case, I just took a different value for the critical effect size than the one that is a default, which was 5%, and then it basically asks you to justify. In fact, I would change that, and I would say, I always ask to justify in the case of continuous. There is a flow chart, there is the guidance. It shows then the results as well. What are the results of the preliminary test? In this case, just testing the constancy of variance, of the constancy of a coefficient of variation, and the test of goodness of fit of the model, if there is at least one model that fits well the data. And a table with the model averaging, and the table with the credible interval for each of the models, and the weights that they receive. And then all the plots that were then presented in the application. Okay? There's the credible intervals, the weights, and then the different model fits based on the normal assumption, on the log normal assumption, all of them together, and the model averaging.
And it's a Word file.
Yeah.
So you can use that as a template and add your comments, what you have done, and your justification. So I think it's really a handy tool, and I really would like to ask you, if you use that tool, use this report button, because if you have to copy it from the figures, it's very likely, at least for me, it's very likely that either I make a mistake or I forget to copy something which later on I won't remember. If you click on download report, you have all the things you have done, even those things which you have done faultily. So you have the chance to recognize it later on, as I did when I used it first. I say, hey, Jose, I get different results. And then he said, well, look at this. And I said, oh, I forgot to tick the Laplace, the other one. So it's really, really helpful.
Yeah, but also it helps you to harmonize, because then we create a report that everybody has the same kind of format, okay? I mean, the justification might be different, but the format is the same, because we can just reproduce your analysis. Okay. Is
And
there any
that was
question?
something which was not present in the past. Well, in the last version it was already there, but in the early days, sometimes you get a BMDL value and you have no clue how they arrived to it, and that's past. So use this report item, then it's harmonization. Now, who has for? I think there is one in the back first.
Thank you. Thomas Backhaus, University of Gothenburg, also representing the Share Committee from the Commission. Just one question. I mean, the tool seems really nice and nice to play with, but do you have plans, or is there a way to also get an R package made out of that? Because I think that would make things really shine, literally, because then you can implement that in your own data analysis pipeline. That also makes the documentation and the literate programming far more easier and for the sake of transparency and things like that.
There is an R package already, and the R package is on another repository that we have in EFSA that is called Knowledge Junction in Zenodo. These things are also there, that you can find the R package already there.
One over here, and then you.
Thank you for this illustrative example. The only comment I would have, this really, really helps if you look at the data, because there's a level of uncertainty. But why is this level of uncertainty where the BMD analysis helps? Because the study is not what it's supposed to be. It has no NOAEL, right? It has effects at the lowest dose. It's not designed as a normal study would look like. Now let's assume what would happen if the study would look like it should be looking like. So the low dose has no effect. Then it would jump from no effect to maximum effect. And then our BMD 10L, according to my understanding, would be far, 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 far lower than the low dose in the study, because the mathematics will kill you due to the big variability, right? So here, this illustrates it. If now the second dot would be right at the same level as the control.
Yeah, but this doesn't mean that there is effect there, because you see the confidence intervals are overlapping. Because why do you say that there is no, that
But you have a graduation. You have something, right?
Yeah, but only on the mean. If you look at the
Only
variation,
yes.
they are very much overlapping. I am not certain that there is not an effect there.
Yes, but if there was no effect and there was really a jump from 0 to 100%, the mathematics would drive your BMD 10L below the lowest dose tested, largely below, right? And then I don't see the beauty of the approach, because in the end, that's the point where I'm trying to get to. In this case, it helps because it defines this little uncertainty and it scrapes out this uncertainty. Is there now something at the low dose, yes or no? And what is a conservative approach? So here the BMD 10L really helps us to set a dose level in this setting here. But if there is seriously nothing, then the BMD 10L will be far below the lowest dose. And what does it give us? That's the point. That's the potential where I think it's really making our life difficult for not a lot of gain. This example for me is perfect because it shows where it can help. It reflects the uncertainty which we have.
My simplistic answer to this would be, don't just trust the computer. Just look at the data and then you see that there is nothing.
Exactly.
And
how,
the tool
how do you
helps
do
you
that?
to tell you if you are not able to look on it, the computer will tell
if it
you
would be
that
the
there
case
is no
that you are
dose
just talking,
relationship.
sorry, if it would be the case that you are just talking about, yeah, that the second dose will be just, they are close to the other two doses,
Exactly.
yeah?
No, to the first one,
If
to the
if
control.
it is close to the first one, then you have two doses that are having no effect
Nothing.
as the control one. Then it would be somewhere in between the first and the second dose. Would not be below the first one.
The BMD 10L would be below the first and the second dose, right? So between the
No,
two
not
bots.
necessarily. It depends on how big the effect is. Okay, it's not necessarily true. There's a
I'd like to
in fact, if the first two doses are having exactly the same response, you know, and the other doses are having a very high jump, you know, your BMD and BMDL are going to be between these two doses. Okay, are going to be between these two doses. If the jump is not that big, then you might end up with a BMDL that is below the first dose that tested. Okay, but that is not necessarily true neither. Okay, the BMD will tell you something about that. In fact, the data suitability will also say that these data contain enough information to estimate the BMD with certain level of reliability. Does I mean, and it will only flag you that, only that. But yeah, I think it's better to model it. Whatever you are doing is better to model it than to try to argue something without having the knowledge of how the models look like. There will be uncertainty around the model between the second and the third dose because you don't know how it goes there. But still, you will have more information than just using an NOAEL approach. You will have information about the uncertainty. You know that the data is basically having uncertainties on where should it be. You know, in the case that you use the NOAEL, you don't know how uncertain is that NOAEL.
Yes.
If I may,
I'd like
I think it's also a problem of the current test guidelines. They are not made for benchmark dose modeling. They are made for statistical evaluation and detection of a no effect level. If you have a situation where you have more doses, then you get more information in the area where you expect the BMD, and then you don't have this problem. The problem arises with this kind of data where you have 3 data points, maybe 2 just no effect, and then 1. So this is probably going on for a while, and not daring to say how long it takes to change OECD guidelines, but this would be probably something for the future to adapt it to this approach where you have perhaps fewer animals in dose group, but more dose groups, which then would allow to have more data points and more informative dose response. There was another...
Just one addition, I think. If there is other information available, the prior can also help in those cases, especially on the BMD. So that's an additional strength should use.
Yes. And I think we know very well how to do BMD studies because we do them for US EPA for many, many years. They have 5 doses, they are titrated around the effect level. The problem for me is this discrepancy in the system because we now have a lot of upfront setting up of the model, but that's not a dialogue, right? The one who does the study needs to know what the endpoint of concern is to design the study. But that's nothing we can solve here. But I just want to point this out because when I look at this data set, most likely it's not going to give us added value, and that would be a shame because here this shows how beautiful it can be.
There is another question from a lady behind there.
I assume I can only ask one question, right? Then thank you for the interface because it looks very convenient to use and it generates a simple report. But for implementing the Bayesian approach, I can see there are many hidden details that I cannot see from the report or from the interface, like how many Markov chains you have, how many sampling chains you have used, whether they have converged or not. Those things, it just... Okay, I didn't see that part. But how can I, do you have like a convergence check in the end? Implement.
Everything is there, but you have the R package. Thus, you can know everything.
So the R package I will obtain.
It's available.
Okay, good.
Yeah, and you have also a report that if you look at the site for the workshop, there is also documents section. There was the agenda and then other documents. That was the guidance document and this document that contain all detail about the application.
Yeah, I
All
saw
detail
the
about the
documentation, but I didn't go through it.
Ah, okay. Yeah, no, it's a bit extensive, 150 pages. You see 150 slides.
Okay, thank you.
Just behind you, there is another question.
Thank you. My name is Evgenia. I'm an epidemiologist and a member of the Quantum panel. Could you briefly comment on your experience so far with the modeling process for the human epidata with regards especially to the distinction between the use of individual study participant data versus aggregate data and the use of covariates and whether and how the modeling process and the tool can accommodate for that? Thank you.
EFSA is asking for a guidance for the use of the benchmark dose approach with epidata for 10, 15 years by now. And it's on the work program for
2023, 2025.
Okay. It's up
that's
there.
the starting date, not the finalization of the guidance.
No, but to be frank, I think, as you have seen, when starting with this, most of the, at least, guideline study, I know in quantum it may be different, but in most other area of EFSA, you are dealing with these standard sets of data, and these are most of the time, or yeah, it's mainly experimental animal data. And as I hope I have shown, it started off with quantal data, then it went to continuous data, and there we entered into troubles. What to do? And I think we needed to solve first the most burning points. And yes, I know for quantum it's burning and cooking for many years by now, but that's the way it is. And yes, hopefully in 3-6 years' time, there will be a guidance how to use. And in the meantime, you have to ask Jose to help you. And
As we already do.
As you know, even in the very early days, we used sort of benchmark dose. Well, it wasn't called benchmark dose modeling at the time, but we used modeling with cadmium and beta-2 microglobulin excretion, but it wasn't called benchmark dose modeling. It was a sort of with human data, and it's always tricky, and I expect also some troubles when that starts. So I agree there is an urgent need for guidance, but we are not there yet. Let's hope that with this update of 2022 for the experimental animal data, we'll solve a lot of the problem we had with constraints of models. And you see now you have all these kind of options which allow you to actually use that information as good as you can. But again, please remember in the end, before you go for coffee, click on the button, download the report so that you know afterwards what you have done.
But just to reply to the question between individual and summary data, in the day of tomorrow, the second day, we are going to see an example in which we are going to use the model with the summary data and with the individual data. There's, in general, for the distribution that we are using, which are normal and log normal, the summary data are sufficient statistics, as it means that they provide the same information as the individual data, more or less, you know, to build the livelihood. Huh? For control experiments, yes. But you are reflecting with I mean, when you are looking at summary, you know, of individual data, that is still, I mean, if your summary data or your individual data that you are collecting is not representing the endpoint that you would like to represent, or if there is other confounding factors, that is different, okay? But if that data is representing the endpoint that you are going to look, taking individual data or summary data is representing exactly the same thing in this context, okay? Because that is not a problem. The problem it is that, I mean, summary data might hide other confounding factors that you could see in the individual data. I mean, the effect of confounding factors that you could see in the individual data, and you are not able to control for then when you have the summary data. Imagine that you have for those group, and there is how do you say, a covariate effect, female and male, but you don't have the data summarized at this level, then of course the data that you contain is not going to provide you any information if there is a difference between these two genders, okay? Thus, okay.
Is there any other burning question? Because we are already, yes, one over there. Kathleen.
Thank you, Kathleen Baert, European Commission. Thank you to all the speakers for the very interesting presentations. I understood that one of the interventions that also expert knowledge elicitation can be used as a source of information for the prior distributions. Now, I was wondering, are there restrictions on this given the influence on the outcome, particularly in the context of trying to avoid divergent views between different agencies? And I was also wondering how this relates to uncertainty analysis, because also there, expert knowledge elicitation is done. There is also asked there what would be the true BMD. So how do you split that? And is there now already part of the uncertainty addressed in the BMD? That was not completely clear to me.
Well, remember that this process should be done before you do the analysis. You need to plan this in advance, okay? These things is just to inform your analysis, okay? The uncertainty analysis is once you do the analysis, no? At that point it starts, okay? How uncertain is the analysis that you perform. This is just before you do the analysis, okay? Before you do the analysis, you assess what prior information you could use to inform the analysis of the data that you are going to collect, okay? Or the data that you are basically going to analyze. These are in two different phases, okay? I don't think that you are going to just use expert knowledge elicitation to, assess the BMD parameter to be used as a prior distribution in your analysis, okay? After you have done the analysis. You do it beforehand, okay? But also that information, I mean, in terms of the BMD, it's very difficult to do expert knowledge elicitation. Something that you could use to inform your analysis is about the background response that you can get, okay? The maximum response that you can envisage for that specific response that you are studying. These are the things that you can inform in the analysis itself. We have included the BMD because if you have done an assessment of that specific substance before, you can use that information to inform the successive analysis, you know? Because it's now becoming a cycle. Then the posterior distribution of one analysis could become the prior distribution for the analysis of subsequent data. Okay? Thus, in that context, we have put that prior distribution for the BMD. You use the analysis that were performed before as a prior information to inform the analysis that you are going to perform today. Okay? The other ones, I mean, background response and maximum response are very important as well to inform the model, especially in those data that you don't have yet reached a plateau, you know, the maximum response. The maximum response, if you just only have the first part of the curve, you know, you don't know where the maximum response should lie, okay? Thus, in that cases, it's very important to get some information about that. But I told you. We put an example in the guidance that we say if you have done a previous analysis on the BMD, you could use that as a prior distribution. We have put that example. Okay, we have put several examples. We have not been, how do you say, very explicit on everything that you can do because it depends a lot on the situation that you are dealing with. Oh.
Okay. One more question here.
The cocktail is going to be very short, eh?
We can extend the deadline, the ends.
Okay, I try to keep it short. So Joachim Noppe from BSF. I have a question regarding the discussion on informative priors to be set. So in the recent guidance document that was just issued for boats and mammoth risk assessment, it's mentioned that BMDs should be used in order to set the reference points, and it is also mentioned that the priors have to be discussed beforehand with the authorities. So I wonder if any process has been thought about on how this can actually be achieved.
I don't have any answer to that. Sorry. I don't know if there will be, but probably they will envisage a process for this. I mean, I cannot imagine that they are asking something like that and then they don't have the process to be able to channel that specific which. Well, the guidance was published, I think that very recently. I even didn't know that that was one of the things that they were just wishing.
Sure. Alberto Linguadoca from EFSA.
You need to go down.
Yeah, sorry. I don't know exactly in specific scenario you're envisaging. Of course, EFSA is not the only authority that is dealing with the risk assessment, so it could be a specific case. But we do have platforms to forward questions to ask to EFSA, and this is through the Ask EFSA. There's potentially a way to communicate with us during the pre-submission advice.
Well, another way to do it is you provide us with your contact details. We will check with our colleagues exactly what is meant with this sentence, and we will come back to you.
No, I think it's just a matter of informing, so justifying the use of priors in a strict manner. But
just to remind you that there is also an opportunity during the networking cocktail to ask these questions directly. And I would like now to call on Marco Binaglia to give a short introduction for the exercises of tomorrow.
Yes, I had the pleasant role to have the simplest and shortest presentation of today. I think you won't be disappointed due to the quite intense sessions. So, just an insight of what will happen tomorrow. This is the agenda. As you can see, basically, we'll do practical exercises on the tool and the guidance. A few words about the setting. So you will be divided in groups of about 10 to 12 people, I understood. And each group will be with an appointed facilitator. The role of the facilitator will be to be the one operating with the tool. There will be one computer basically for each group. And you will be presented with 5 exercises. And we will, actually, Jose will run the exercises first. So we will show how to perform the modeling for all the exercises. And And then it will be up to you to replicate, basically replicate the analysis, okay? Following the instruction given before by us. Yes, the objectives of tomorrow will be really to have hands-on practice on the tool, to have a practical application on what was presented today about the guidance, with real data set or data set that are inspired to real cases, to get insights of how to analyze the model outputs, as we show, as Jose just showed a bit in the previous presentation, and to look also at basic functionalities of the tool. Are also advanced. We look at covariate analysis, prior information, so we have the chance to apply all this in practice. Yeah, about the 5 exercises, we try to cover both examples from mammalian toxicology studies and environmental toxicology studies. So we take examples from both areas. You can see here the description of the studies we will model. You have seen something already, a bit of a spoiler already today. All the examples actually come from the pesticide area, but this does not prevent, because actually the endpoint we will model are very standard endpoints, and the study we look at are very standard type of studies that can be actually encountered in all areas, regulatory areas dealing with human health risk assessment or environmental risk assessments. So this is really useful for also for colleagues dealing with all different areas, including contaminants, food contact materials, etc. Also beyond EFSA's remit, possibly. I think this was my last slide, so I was really quick. I guess there are no questions, but...
If you have any questions to Marco, I would like to defer them to 9 o'clock tomorrow.
Yep. Very good.
So thank you very much for the lively discussions. And yes, I would like to close the meeting for today, and the cocktails are served outside for those who came to Brussels. Good luck for those on the web. The meeting is closed.